legitimate claim to be regarded as the most accomplished and influential theoretical physicist of the second half of the 20th century. And so one can easily lose the lead in all of the things that Phil was involved in. So let me start immediately with that. This is what I would regard as the punchline, is that Phil Anderson was a brilliant intuitionist who did more than any other person to transform the patchwork of ideas and techniques formerly called solid-state physics into the deep, subtle, and intellectually coherent discipline known today as condensed matter physics. And he presented his grand synthesis, or at least as it was at that time, in this famous book in 1985. But of course, even this is just a fraction of what Phil was involved in. And to get a sense of that, it's interesting to try to graph it. And so here's a plot of from 1950 to 2000, actually beyond 2000, all the many things that Phil was involved in. He had over 600 publications, and so this is a tiny fraction. But if you this is meant for shock value. I can't even read all of these and say 15 seconds about them without running out of time. But you can look and see that many of these things fall into this category that we call many-body physics, but not all of them. And in fact, he was quite proud of some of the one-body problems that he worked on as well. My talk today, I'm going to focus mostly on some of the earlier years, just assuming that most of the audience are younger folks and they're more familiar with what Phil was up to in his later years. And I hope that will give us an opportunity to see some sense of what he was about. So here's where everything sort of starts. Phil was born in 1923. And so this is a family photo from 1934. There's Phil up front, his mother right behind him, his sister, Graki, she was known, Grace in the family, and his father, Harry. Both sides of the family come from Indiana and migrated to Indiana in the 1850s, in fact, in two adjacent counties in Western Indiana. But in fact, and most of the family, in fact, lived there, and Phil and his family visited them quite often, but because they didn't live there, they actually lived in Champaign-Urbana because Harry was a professor of plant pathology at the University of Illinois. And so Phil grew up there, although the family went back very often, particularly to Crawfordsville, because that was the site of Wabash College, which is where his grandfather was a professor. So he actually is a third generation academic, if you like. The photograph here in 1934 is significant because this was the time of the Great Depression in the United States. But it's important to realize that the Great Depression did not seriously affect the Andersons. And this was because Harry was a professor, and it's not perhaps well known, but professors across the United States at universities didn't do too terribly badly during the Depression. Very few of them lost their jobs, and most took about a 15% pay cut. And that was the case with Harry in 1933, but he in fact rapidly earned it back. And so Phil had really a rather nice growing up, I would say. He didn't have to have a summer job, say, to help support the family. They took vacations. Harry bought new cars every few years. And so he was able to focus on academics, in fact. He did that at the University of Illinois Laboratory High School, which is shown here. This is one of these high schools which is created by a university for the purpose of providing a place for their College of Education folks to learn their trade. And Phil was a student there and did extremely well, actually, practically straight A's. And he was also an athlete. He was on the track team, he was on the tennis team, and he was also a speed skater. The principal influences on Phil as a high school student were these two gentlemen. Miles Hartley was the math teacher. He taught him geometry, trigonometry, and calculus. Hartley was a real innovator, and he published in the mathematical pedagogy literature as well as in the technical literature, and inspired most of his students. And Phil, in fact, planned to become a math major on the basis of Hartley's influence. This gentleman down here, this dour fellow down here, is Wilbur Harnish. He was Phil's physics teacher. he was sort of the anti-Hartley. He had no training in physics at all. All of his training was in education, and he was given the physics class to teach. And his method was to roll out the experimental equipment, pumps, pulleys, motors, and have the kids play with them. There was practically no theory whatsoever. And one of Phil's classmates told me that everybody left Harnish's class detesting physics. So perhaps that's reinforced Phil's idea to become a math major. He went on, in fact, to college, and he was able to do so at Harvard University, in part because his father was quite friendly with a number of the physics department members at Illinois, in particular Wheeler Loomis and others, who encouraged him to apply for a scholarship, a free ride scholarship that Harvard had just created and very recently for the purpose of diversifying their student population. So it was aimed at kids from the Midwest and the West. And there's an interesting story there, which I can go into in more detail if anyone is interested. But he did, in fact, matriculate at Harvard, and he was there from 1940 to 1943. It's only 3 years because after his sophomore year is when the war broke out, World War II. And Harvard restructured their curriculum. They added a summer semester. And they, in addition to their physics major, which they already had, they created a major called electronic physics, which they encouraged their physics majors to switch into, which the curriculum here would be what we would call today radio engineering. And the idea was to prepare their graduates to immediately contribute to the war effort. And in fact, Phil, who's shown here as a freshman, he started in math, as I had said. He had switched to physics as a sophomore, and then he switched to the electronic physics program so he could immediately start contributing to the war effort. Again, he did very well as in sort of classwork, and his main competition, in fact, the gentleman who was sort of the boy genius of his class, was this fellow, Thomas Kuhn. And if that name is familiar, it's because he is in fact the same gentleman who wrote The Structure of Scientific Revolutions, that famous book. He turned to that after actually he got his PhD, but he was a physics major with Phil, and they actually were friends their entire lives. So as I say, Phil was this electronic physics major. That meant that he was going to go work at a radar facility. There were physics majors still at Harvard, and they all got shipped off to Los Alamos, even though they didn't know what was going on there. That's in fact where they went to work. So what radar facility did Phil become associated with? It was the one that was set up at the Naval Research Laboratory. So he was there from his graduation to the end of the war. And he was attached to an antenna group, a microwave antenna group, and in particular, a group that was designing antennas to do radar countermeasure work to be mounted onto ships. So for example, at a certain point in the war, the Nazis developed a bomb which was dropped from an airplane and then radio controlled to its target while the airplane itself still stayed way out of range. And this was wreaking havoc in the Mediterranean, and the Naval Research Lab rushed to the Mediterranean to detect what the frequency was. And then Phil's group, which was an experimental group, designed this antenna for the purpose of jamming that signal. Now, one of the interesting things about that electronic physics major is, as I said, it was basically radio engineering. So there was no, what you might call 20th century physics in there. And in particular, there was no quantum theory of any kind. And so Phil's first brush with that really came at the lab, Naval Research Lab, when an older scientist there bought a book, which was brand new at the time, The Mathematics of Physics and Chemistry by Marganow and Murphy. And it had several chapters on quantum mechanics, which Phil devoured. In fact, he devoured the entire book. It's actually, I own it myself. It's a very interesting book worth looking at. But I think the interesting thing is what's in the introduction to this book. This sentence appears: the successful pioneer depends more on brilliant hunches than on the results of existence theorems. So if this either resonated with an idea which was already in the back of Phil's mind, or perhaps it launched him on an attitude which he carried with him his entire career, which is that intuitive thinking was much more valuable than formal mathematics when it came to physics. In fact, he really opposed, or I should say, he really did only as much mathematics as he needed to do to convince others of something he knew was correct intuitively. And this is a hallmark of his career. So the war comes to an end, and Phil has by then decided he wants to be a professional physicist. The work here convinces him, by the way, that he doesn't want to be an experimentalist. He doesn't have the hands for it, and so he looks to do theory somewhere. Nuclear physics would have been the appropriate choice to work in because that was the hot topic, and there were lots of places to go one could do that, but he didn't do that. He felt that Harvard had robbed him of an education in 20th century physics, and so he was determined to go back to Harvard for graduate school in order to extract it from them. As it happens, at Harvard at that time, 1945, there were only 2 faculty members for which one could do a thesis in theoretical physics at all, which we'll come to those gentlemen in a moment. I'm just showing here this time at Harvard from 45 to 49. This is the physics department. Before getting to the thesis work, he was taking classes, took a lot of classes. Thomas Kuhn went back to Harvard as well, and they continued their friendly competition. Another entrant into the academic competition was this gentleman. This is Walter Cohn. This is a picture of him the year before he goes to Harvard. He's in a Canadian Army uniform, and it's an interesting story of how Walter, who was born in Vienna, wound up in the Canadian Army. And I can talk about that later if anyone is interested. More interesting maybe, and they of course, their competition, let's call it, continued, I would say, friendly competition through their entire careers. Phil did not hang around, actually, with the other physics graduate students. He hung around with a completely different group of people who included this gentleman named Tom Lehrer. Now, if you're of a certain age, like my age, you can not only know who he is, but you can sing all of the songs that he wrote and performed, accompanying himself on the piano. Basically, very soon after this time, he became a national and actual international star, writing satirical songs which had a great biting social justice content to them. They're actually as meaningful today as they were when Lehrer performed them. And for those who don't know his name, I strongly recommend you look up websites which are devoted to his music, and you'll hear him play. And it's quite remarkable. He and Phil remain close friends, actually, for Phil's entire life. And Lehrer was still with us, in fact. So I was talking about mentioning the possible thesis advisors. Here are the 2. Now, Julian Schwinger had just arrived at Harvard at the same time, basically 1 semester before Phil did. And he, of course, was the wunderkind of theoretical physics. Harvard had outbid everybody else for his services. And in Phil's class, almost everybody who wanted to do theoretical physics, and there were 11 of them, went immediately to Schwinger, and he took them all on as students, including Walter Cohn. Phil, demonstrating the contrariness, which was another feature of his personality, when all these 11 folks were swimming downstream, Phil turned around, swam upstream, and decided to work for the other theoretical physicist in the Harvard physics department, and that was John Van Vleck, who at that time was the chairman of the department. Van Vleck had made his career writing, or his reputation, writing a book on electric and magnetic susceptibilities. He was an early user of quantum mechanics in the United States. But at this time, he was mostly interested in spectroscopy because radar equipment that had been developed during the war was now being used in physics laboratories to do spectroscopy in the microwave, which had been a largely inaccessible part of the spectrum before that time. And that meant actually molecular spectroscopy by and large. And so Van Vleck became very interested in trying to be quantitative about that particular topic. He was a tremendous believer in following the data. And this is where Phil learned another aspect of his entire scientific career, which really set him apart from many other theorists, and that he was extremely interested in experimental data and grappling with it down to the level of raw data understanding exactly how experiments worked. And this was a tremendous advantage to him. And Van Vleck was the same way. Phil tells a story of going to New York City with Van Vleck, and they walk into a room and all the experimentalists rush to Van Vleck waving their data, trying to convince Van Vleck that he should listen to that person and help them understand what was going on. The particular problem that Van Vleck gave to Phil was this. So this is an experimental spectrum of absorption in the microwave. This is about 1 inverse centimeter here of ammonia, the ammonia molecule. And his task was to construct a complete quantum mechanical theory of the line widths of each of these lines, taking as much account as he possibly could of the collisions between different ammonia molecules. So the phenomena is called pressure broadening, and he was to make a quantum theory of that. In fact, the theory of spectra at that time barely was quantum mechanical at all for problems of this sort. It was essentially classical. But Phil succeeded. He actually used things he learned from a class he took from Schwinger and applied those to this problem. So he predicted the widths of all these lines, and the agreement with the data was quite good except for 2 of those lines. And in his thesis, you can read that with regard to those 2 lines, he suggested that there was some experimental error. Quite a bit of hubris, I would say, for a PhD student, but it turned out that he was right. Now, this work was done essentially all in his very last year at Harvard. And right before that happened, he had gone back to Urbana to visit his family, and his life changed because he was introduced to Joyce Gothwaite, who we met in June of 47 and then married in July of 47. And so I think this qualifies as a lightning romance. Their daughter, Susan, was born a year later, and by absolutely all accounts, they were a love match, absolutely devoted to each other their entire lives, a remarkable marriage. Joyce really dedicated herself to her husband's success and doing everything she could to, particularly in his time at Bell Laboratories, to not only be a hostess and more of the conventional things you might expect, but telling him how he should talk, how he should what clubs he should join, what he should wear, everything for success. She also, being an English major and an MA in English literature, edited his prose work for most of his life. And so much of that good writing in the prose pieces owes a great deal to Joyce. So here is Phil. He graduates, and he's worried that a postdoc job won't pay enough to support himself and a new wife and a new baby. And so he only looks for academic jobs and industrial jobs. And in fact, the only one that he gets an offer at that he takes seriously is a job at Washington State College in Pullman, Washington. It doesn't even have a graduate program, but that's the job that's available. He buys a car and is about to drive out there when Van Vleck asks him, "So, Phil, what are you going to do with your PhD?" And Phil tells him, and Van Vleck asks if that's really what he wants to do. And Phil says, "No, I'd rather go to Bell Labs, because when I was at NRL, the best equipment that we got was from Bell Labs, and the best expert advice we got was from Bell Labs." But he couldn't get an interview at Bell Labs. Well, like then, like today, it helps to know people. And Van Vleck just happened to be a consultant to Bell Labs. And so he called up his buddy, Bill Shockley, and said, "Have I got a student for you?" And so Phil got, in short order, an interview. And in fact, Shockley chose to hire him. So Phil starts his career. This is his first year there in 1949. And he has a long, very successful career there. And it's important to point out is the golden age at Bell Laboratories, where it was probably the best place to be a solid state physicist in the United States and maybe in the world. It grew to be an enormously successful laboratory, and Phil's sort of growing up as a scientist was coincident with that, which I think is pretty important. Shockley had an ulterior motive actually in hiring Phil. He had a pet theory of ferroelectricity, which he wanted someone to work out the details of. And that's in fact what he asked Phil to do when he arrived. Phil did that, but sort of became disenchanted with the problem relatively soon, and became disenchanted with Shockley because Shockley was a difficult guy. He and Bardeen and Brattain had discovered the transistor quite earlier, just a few years earlier, and Shockley had fallen out with both of them, and he was just a very, very difficult fellow, and in fact soon left the labs. And so Phil started looking around for other mentors, but Bell Labs was the fantastic place to do that. He barely had to take 25 steps, and he ran into 3 superior theoretical physicists that he could learn from. He actually shared an office with Gregory Vannier, and Conyers Herring and Charlie Cattell were not far away. Now remember, Phil wasn't trained in solid state physics. He was trained as a chemical physicist. And so these gentlemen really taught him, all of them about 10 years older than Phil. And so perfect mentor figures. And they really taught him solid state physics, different aspects of it, each one of them. When it came to research, Cattell got him interested in magnetism, and in particular, antiferromagnetism, because right at that moment, neutron scattering was being developed for the purpose of studying magnetic structure, and the very first data was being generated by Cliff Scholl for that. And this, in fact, was the source of Phil's first success, was to explain the neutron scattering data, or I should say, the magnetic structure that had been come out of that. And for that purpose, he developed a theory of what's called superexchange in order to predict that structure. This impressed a lot of people, and it was enough to generate his very first invited talk at the 1950 March meeting of the APS. That really launched his career. He became fascinated by antiferromagnetism and worked on it quite a bit in those early years. And in particular, most of the theory that was going on was actually classical and barely even semi-classical. And so he decided to try to construct such a theory. And he did that with this paper here, an approximate quantum theory of the antiferromagnetic ground state. An interesting paper, which was interesting to both theorists and experimenters, including Wolfgang Pauli, as it happens. But from a historical point of view, the most interesting part of this paper is the very last section, where he discusses a phenomenon which we today call spontaneous symmetry breaking, although nobody called it that at the time. And in fact, nobody picked up on that part of his paper for over a decade. People refer to this paper for various reasons, but not at all for this particular aspect. One of the people who was interested in the other aspects was Ryogo Kubo. And so this is Kubo right here. And he and Phil met at a meeting in the United States, and they hit it off very well. And Kubo decided that it would be nice to have Phil spend 6 months with him in Tokyo with his group. And so he arranged for the Fulbright Foundation to pay for that 6 months, and Phil convinced Bell Labs that it was a good idea for him to do that. They wouldn't have to pay, so they liked that. And the clincher was that there was the Japanese were organizing the first big international meeting of theoretical physics after World War II, in part for the purpose of rehabilitating their reputation. And that is, in fact, the conference that the visit was piggybacked on. So Phil went to this conference and then did, in fact, spend 6 months with Kubo, very successful. But really, the main thing which to take away is that this conference is where, because he was an unknown, Phil was completely unknown at this time. But at this conference, all the major theoretical physicists in the world were there, and Phil realized that he could compete with them, or he could hold his own with them, and that was a tremendous boost for him. So when he returned to Bell Labs, and he really felt that he at that time could start building an independent career. His method always was to see what was going on experimentally, and when he returned, what was going on was that a brand new hire from Berkeley named George Fair had started studying doped silicon crystals, because most of the transistors at the time were made of germanium. It was understood silicon would be interesting, but not much was known about it. And so one of the things he was doing was studying magnetic resonance in these samples. And in particular, he learned from his, just looking at the data itself told you that the donor electrons, the extra electrons, in his case associated with randomly distributed phosphorus atoms in a otherwise perfect crystal of silicon, did not seem to hop from donor atom to donor atom, or tunnel from donor atom to donor atom, as quantum mechanics would tell you. They did not appear to be mobile in that sense. So he got Phil interested in this, and other theoretical visitors to the lab. Neville Mott actually came through and suggested a mechanism based upon electron-electron repulsion. That is to say that an electron on one donor site wouldn't hop to another one if there was already a donor electron there, because the electrical repulsion would be too strong, and that would inhibit that hop motion altogether. And at the end of the summer, the various visitors who were there agreed, yeah, that was probably what was going on. They left. Phil was left behind and didn't believe, right? Left behind, still at the labs, of course. And he didn't really believe this mechanism for various reasons. And as is well known, he then went on to discover the phenomenon we today call disorder-induced localization. And this famous paper, Absence of Diffusion in Certain Random Lattices, is where he describes that work. The thing to know about this piece of work is that it was either disbelieved by most people because it violated what people thought they understood about quantum mechanics, or what happened mostly is it was just ignored. Nobody was interested in the issue at all. From our point of view, the model that he developed for this problem is characteristic of, again, one of Phil's great strengths through his career, which is to take a complicated problem. I mean, this is a silicon crystal with randomly placed phosphorus atoms, and one's trying to understand the wave function in this disordered thing. He did not try to even begin to make a model of something like that. He instead took a complicated problem that he had, and he progressively stripped away all the parts of it which were not essential to what he was trying to understand, until he wound up with a simple mathematical model that only bore the most crucial resemblance to the original problem, and then he studied that. And this is something that he did through his whole career, which is why there are so many Anderson models. They all have that characteristic. And of course, this set of lithographs from Picasso gives that same sort of notion. Now, Phil was writing up the localization paper when Bardeen, Cooper, and Schrieffer announced their proposed solution for a microscopic model for superconductivity. And this got everybody's attention, including Phil. And he actually stopped writing the localization paper to work on this. And interestingly, one of the very early issues in superconductivity was a formal question associated with gauge invariance. I don't know if you can read that. It's in the way. There we go. Gauge invariance. And the important thing is that Phil never questioned that BCS, he never thought they could be wrong. He was certain they were right. Why? Because they had all the phenomenology right. All the experiments, it had the right features. And so he was convinced that this was one of these formal mathematical things that couldn't have any important physics content. And in fact, he proceeded to demonstrate that before anybody else did. And this paper got the attention of everybody, particularly Bardeen and others. Phil really became enamored with superconductivity. He later called it the love of his life. And so very soon thereafter, this is January 58, July 58, he does a very beautiful piece of theory, the random phase approximation in the theory of superconductivity, which is focused, among other things, on looking at the collective excitations, the excited states of the superconductor, where many of the particles move in concert rather than individually. Very beautiful piece of work, which really expanded his reputation internationally and outside of the magnetism community. He had an opportunity just a few months later in that winter. Charlie Cattell was arranging one of the very first scientific trips for scientists, American scientists, to go to Russia. And he recruited Phil to go with him. And Phil talked about this work at Lev Landau's famous seminar, where they're famous for ripping people apart. But in fact, Landau approved. And Phil became a fan of Landau's since that time. So Phil comes back. He is working on a variety of things when Neville Mott contacts him and says, hey, how about if you come and spend a sabbatical year at my university, which is Cambridge University in the UK. And Phil is tempted and he asks, can I teach a graduate class? And Mott says, yeah. And in fact, Brian Papard, an experimentalist there, was also very enthused about this. And so Phil went back to Bell Labs and said, can I do this? And they agreed. And so he, in fact, spent this entire academic year at Cambridge. This is the book which came out of the class that he taught. It's a very interesting book because it's very small, but it differs fundamentally from every book on the subject that had been written before, because it talks not at all about the vast phenomenology of solid state physics. It instead focuses on what we would today call a handful of model Hamiltonians on the behavior of electrons and spins in various situations. And so it's very modern to us, but that's because we have adopted Phil's perspective, which he introduced to our world as early as 1962. One of the people sitting in the class, this graduate class, was a first-year graduate student named Brian Josephson, who was actually working with Papard on an experimental thesis in superconductivity. And he got very excited when Phil started talking about breaking symmetry in antiferromagnets, which is in here. He also talked about breaking symmetry in superconductors, which is not in the published book, but we know from oral evidence from people in the class that he did talk about it. And that jazzed Josephson, who was interested in trying to use that idea to measure the phase of a superconductor. And he and Phil spent hours and hours out of class talking about this question. And ultimately, Josephson wrote this famous paper where that predicts the phenomena that we know by his name today. He eventually won the 1973 Nobel Prize for this, or shared it. And Josephson is quite clear in crediting Phil for providing some of the key ideas. Now, while at Cambridge, Phil would hang around the tea room and he would listen to the particle physicists talk about their problems. And one of the problems they had was they were trying to make gauge theories of some of the elementary particle spectrum. And they kept getting zero mass rather than the finite mass, which is, of course, observed. And in a moment of true intuitive brilliance, Phil realized that the physics that had gone into his random phase approximation for superconductors associated with the generation of the plasmon from a sound type wave that he had discovered when there was no Coulomb interaction would be relevant to the particle physicists to generate mass in their theories. And so he wrote a paper which was targeted and addressed directly to the particle physicists, shown here. Plasmons gauge invariance in mass. Peter Higgs was a young theorist who realized that Phil's idea had merit. He simply translated into a fully relativistic language and wrote this paper where he, again, is very gracious in crediting Phil with the basic idea. And as you know, everybody knows that led to a Nobel Prize later for Peter Higgs. And so this 1 year in Cambridge that Phil spent was quite productive. It generated 2 Nobel Prizes, although not for him. So he returns to Bell and instantly starts hanging around the experimental laboratories again. And one of those labs was the one maintained by this gentleman, Bernd Matthias. Interesting, prickly kind of a fellow who most of the time had no truck with theorists at all. He was a real seat of the pants experimenter. And Phil's relationship with him is what Phil called mostly love and some hate. But for our purposes, Matthias was doing experiments where he was dissolving magnetic atoms in non-magnetic metals and looking to see if the magnetism survived or not. And the results were quite confusing and unsystematic. And he got Phil interested in that particular problem. So Phil started thinking, and along the way, he had to go to a meeting in a small magnetism meeting in Britain, but he stopped on the way in Paris. And he met for the first time there Jacques Friedel, who was interested in alloys quite generally and had been thinking about these problems. And Phil, in their conversation, realized that Friedel had actually had many of the crucial ideas needed to understand Matthias's data, but he had misidentified, in Phil's judgment, the energy which was responsible Friedel thought it was the exchange interaction, and Phil realized that no, it was in fact the Coulomb energy that Neville Mott had talked about. And so in this famous paper, Localized Magnetic States in Metals, he fuses together the work of these two folks. He's very complimentary to Friedel, but also very clear in pointing out what Friedel had gotten wrong. In my opinion, this is one of Phil's most beautiful papers. Beautifully written, introduced, the model description, how it relates to experiment, what the future might be, a very beautiful piece of work. And in fact, that's why I think that the Nobel Committee recognized it along with his localization work in 1977 when he shared the prize. Okay, so now Mott is trying to get Phil back ever since the sabbatical year, and he half succeeds in the sense that he induces Phil into accepting a half-time professorship at the University of Cambridge, and Phil convinces Bell to go along with this scheme. And so for quite a number of years, Phil would spend the fall and the winter terms in Cambridge as a professor there, and then he would spend the rest of the year at Bell. This was an incredibly productive time period. Lots of interesting things got done. Maybe Bill Brinkman will talk a little bit about that. I just pick one thing, which I think is particularly significant. He worked on a problem which derived ultimately beginning with the magnetic work with Matthias, evolved into what's called the Kondo problem. And together with one of his first graduate students, Gideon Yuval, and Don Hammond back at Bell Labs, they constructed a rather complicated theoretical description. But what came out in the end is what we would today call a renormalization group analysis of the Kondo problem. And then immediately after that work was published, Phil said, this has got to be an easier way to do this. And he published this paper, which is a truly beautiful description of how one derives the scaling equations for this problem. And this is all before Ken Wilson. And so I regard this as one of this achievement of Phil's as truly remarkable. In the statistical physics community at this time, scaling was understood, but certainly nothing like the renormalization group. And it's quite a thing. At Cambridge at the same time, Phil developed an interest in sort of science and society more generally. He and Volker Heine co-taught a course on this subject, and Phil decided to go public with some of his concerns. And so he published this article in the New Scientist magazine, Are the Big Machines Necessary? My doubts about the level of worldwide support for high energy physics have grown. I question the wisdom of shutting down smaller scientific projects to fund the construction of large particle accelerators. So he's going public with a criticism of the particle physicists and their big machines. Now he makes the mistake in this article of attacking the particle physicists on their own ground. And he makes some small mistakes, and they don't know who he is anyway. And so there's really this article kind of drops silently and disappears. A year later, he takes a different tack and publishes this famous paper that Pierce mentioned, More is Different. It actually has similarly an attack on the particle physicists, but he does this by promoting his own work and being silent about theirs. And here's what he says. The behavior of large aggregates of elementary particles cannot be understood in terms of a simple extrapolation of the properties of a few particles. So he's attacking the concept of reductionism that the particle physicists had been selling, that, well, once we understand all the elementary particles, building everything up, that's a trivial step. We'll leave that for others. Phil goes on, at each level of complexity, entirely new properties appear. This is the concept of emergence, the understanding of which requires research, which is as fundamental as its nature as any other. And so he's making the point that, again, the particle physicists do not have a hammerlock on what's fundamental. They just don't appreciate other aspects of fundamental, and I'm pointing them out. And so we have this notion of emergence, fundamentality, and the destruction, in his view, of reductionism. Very important paper, which attracts a great deal of attention. As it happens, some of the ideas had been developed in the philosophical literature, and so philosophers were particularly interested in this, but as other scientists in physics and in other disciplines as well, and then it moves into all kinds of other fields. And I'm just illustrating how important it ultimately became by showing you a couple of books which happen to be edited entirely by philosophers, although there are scientists contributing to both of these volumes as well. So this is an interesting thing for sure. Around this time, Phil and Joyce decide that the transatlantic business is getting too much for them, and they decide to come back to the United States. And through the good offices of John Hopfield, he manages to transfer his half-time gig at Cambridge into a half-time position at Princeton, where he then has a long career there as well. And again, many things to be said about that. And once again, I've just chosen one, this famous Gang of Four paper, 1, 2, 3, 4, on localization. Now, I have to say that after his original paper in '58, Phil didn't do a great deal with localization thereafter. And it really is due to Neville Mott, who became the champion for, in fact, coined the term Anderson localization and went around proselytizing, getting theorists, experimentalists interested, and he got David Thowles interested. And it was Thowles's work which ultimately motivated Phil to return to the problem with these collaborators. Maybe Rama will tell us a little bit about this later. Princeton benefited from the fact that just 2 years after Phil went there, the Nobel Committee chose to honor Phil here, together with Neville Mott, shown here, and John Van Vleck there. And of course, Phil sort of is the bridging agent there, working on the magnetism with Van Vleck and with disordered problems with Mott. You can be forgiven, I think, if you were a resident in New Jersey, where, of course, Princeton is, and you picked up the Daily News, and here's Phil and Joyce simulating the phone call from Stockholm, and you can be forgiven if you thought that this was the couple nabbed on the sex ring charge. That was not the case. So after the Nobel Prize, Phil is working on a huge range of different kinds of problems. He becomes increasingly interested in complexity, and that became a real dominant issue in his life when his old friend David Pines, who he had known for a very long time, approached him with the idea to help organize an interdisciplinary institute, which was supposed to deal with problems that fell through the cracks of other disciplines, which ultimately became known as the Santa Fe Institute. Phil signed on and got involved in actually the very first major activity that the Santa Fe Institute generated, which was together, he in fact recruited Kenneth Arrow, a Nobel laureate in economics, to put together a workshop where a bunch of economists got in the room with a bunch of physical scientists. And there you have a bunch of people, all of whom think they're the smartest people in the room, hashing out how the methods of physics might be useful for very complex systems like the economy. And in fact, it spawned what became known as the Santa Fe approach to economics, which survives to this day. Phil himself really found the Santa Fe Institute tremendously stimulating. He really went back for a visit every year, but his engagement with it tailed off compared to the very beginning, because this time is precisely when superconductivity is discovered at very high temperature in the cuprates. And he has early access to the data again, because even though he wasn't at Bell Labs anymore, he had plenty of friends there, and he heard all about it, and very quickly came to an opinion about what was going on, introduced the so-called resonating valence bond state, a pure many-body approach, completely different than the BCS approach to superconductivity. He was quite sure he was right. It played into all of the phenomena that he had worked on in previous years. He got into print before any other theoretical physicist on this topic, here on this issue of Science. And here, just a couple of weeks later, is a picture from the news conference held at the famous Woodstock of Physics meeting in New York, where once again he is describing his theory. He was absolutely elated. He was quite certain that the Nobel Prize would be coming in his way, a second one, in another year or so. Well, that didn't turn out to be the case. He worked on it. This problem became an obsession, I would say, with Phil from this time forward. And he went down a number of paths. One of them led to what he called the theory of superconductivity, published in 1909. Almost immediately when this book was published, it was shown to be wrong experimentally. Phil, to his credit, dumped it instantly and went back to some of his earlier ideas. But he was really quite hostile to other people's ideas about this subject. And it has to be said, he contributed to some of the rancor in that field. He wasn't the only one, but he certainly contributed, and that's regrettable. I want to conclude with two other aspects of Phil's career. One was a continuation of his interest in science policy, and in fact, with these big accelerators. And so at a certain point in around 1990, the particle physics community decided to put all their eggs in one basket and ask the United States to build a superconducting super collider for studying their problems. And there was testimony in which Phil and Steven Weinberg were both present in the room and giving oral testimony on this day. Here's something Phil said. Two recent books have tried to justify the supposed fundamentality of particle physics. The fact that the authors have time to write such books may tell you something about their field. They have nothing else to do. That's Phil. Weinberg, who spoke right before him, if the super collider is killed this year, it's killed for good. And what is killed with it is a high energy physics in America. And that may be the beginning of the killing of support for basic science. Well, a month later, in fact, Congress killed this project. It didn't kill high energy physics, but I think it's fair to say both of these gentlemen were a bit hyperbolic. Finally, I want to just mention that really the last 20 years, Phil has been a bit of a public intellectual, making and writing about science and policy, science and society, science philosophy. And here he wrote an article in a British newspaper, which is sort of like the Wall Street Journal, entitled 4 Facts Everyone Ought to Know About Science. And I'm just going to read the 4 facts, according to Phil. Science is not democratic. Computers will not replace scientists. Statistics are often misunderstood. And good science has aesthetic qualities. And we can argue about if these are an appropriate set and what Phil might say about them. And if you're interested, I've actually written an article in Perspectives in Physics about that. So I'm done. Here's a very nice picture of Phil. And I just want to say that when Phil left Japan in 1954, he presented to his host, Kubo, a Japanese quince, which Kubo planted in his garden. And it flowered every single year. And even after Kubo died, his daughter cared for this plant, this flowering plant. And it did flower every year as recently as March 2019. But as it happens, this picture taken in early March of 2020, that plant finally withered and died. And only a few weeks later, Phil himself passed away. If you're interested in more about Phil, then hopefully Oxford Press will do what they say and publish this book in December. And I thank you very much.
Wow, thank you, Andy. I'd like everyone to unmute their mics and give a big hand to Andy. It was tremendous. Wonderful. And we've got a few minutes before we go to the round table, and I'd like to open everything for discussion and questions and remarks. Please, if anyone has a question for Andy, go ahead and ask it now. If you can raise your hand, by the way, if you're going to do this in the participants, you can raise your hand if you want to ask a question. Well, okay, Jorge, would you like to ask a question?
Hello, thank you for this fantastic talk. I think we'll all have enjoyed it very much. You've mentioned several times a certain intuitive and maybe, I think you used the word contrarian style. And I'm just wondering, your assessment, having looked at his life, is it that physics needs more of that or less of that?
Well, that's an interesting question. there's this fashion and herd mentality. It's not something that physicists are immune to, right? And I think Phil was sort of that idea was up front in his mind, and he never wanted to. In fact, he never did follow fashion. When you look at his papers, he almost never, if somebody else discovers something, he almost never works in that field. He wrote one small paper on the quantum Hall effect, and that was it. And on many other things that other people pioneered, he never worked on at all. He really preferred to find new things, to discover new things. And so that appears as a contrariness in that sense. But the example of not working with Schwinger is an interesting one, I think, because that really he was certainly doing the most exciting stuff. It's hard to see how spectroscopy of molecules would be very exciting, but he did not want to be one of the 11 people standing in line waiting for an audience with Schwinger. And so to answer your question, I think it's good to have some people like Phil, that contrariness, but God forbid if we were all that way, right?
Thank you.
Andrei Nevedomsky, you have a question. You have to unmute your mic.
Yes, can you gentlemen hear me? Yes, Andrew, I have a question. Was you aware of any interactions between Richard Feynman and Phil Anderson? And the reason obviously is because Phil has used the diagrammatic technique in his work, but I'm curious, there was sense of admiration. Julian Schwinger was the same age as Feynman, roughly. And so I'm curious how he thought of Feynman, especially given that the latter was mainly a particle physicist.
Right. It turns out they never, I asked Phil actually, they never met, but Phil was present at a meeting, the second International Theoretical Physics Conference after the one in Tokyo, in Seattle, where Feynman gave us a famous talk actually it was about helium, but he mentions about his attempts to solve the superconductivity problem. And Feynman says that we don't have enough imagination. And Phil actually lists Feynman and Landau as the two theoretical physicists that he most respected. But I should say that Phil regarded diagrammatics as a scourge. He felt that too many people would simply regard the diagrammatic perturbation theory as a crank that you could just turn to get answers rather than thinking hard about a problem. That doesn't mean he didn't use it when he thought it was useful, but he generally speaking did not think particularly highly about that particular approach. But the helium work, for example, Feynman's beautiful work on that was right up, I would say, Phil's alley.
Good. We have a question from Masaki Oshikawa.
Yeah, thank you for very beautiful talk. And I have a small question. So you introduced a famous paper on the scaling theory of Anderson localization, colloquially called as Gang of Four paper. And I'm wondering why the authors are called Gang of Four. Was there any particular reason?
Sure. This was a reference to a political situation going on in communist China after Mao died.
Oh, yeah, okay.
All right.
Yeah.
And so there were four people, including his wife, who were branded as traitors, and they were called the Gang of Four.
So it was just around the same time.
Exactly, yes.
I see. Thank you.
Any other questions? We have 178 people here. There must be more questions out there.
Yes.
Yes.
I have a small comment about Feynman and Anderson, if I may.
Go ahead. Please. Yes, please, Gampati. Yes.
So it was, I think 86, Challenger explosion has taken place. And there was a committee to investigate that. Phil Anderson came to my office early morning and said that they have put Dick Feynman in the committee. I'm sure next week we'll find a solution. Phil was very confident. And next week he did find a solution.
Yes.
Thank you.
Thank you.
Doug Scalapino has raised his hand. Welcome, Doug. What would you like to say or ask?
I'd like to ask about the interaction between Phil and Bob Schrieffer. I was at Penn in the early 60s, and I know the two of them had a number of interactions, and I believe one time I saw a letter from Phil that described how he and Bob, he felt, were the two leaders at that time of condensed matter, where it was going.
Yes, Doug, great to see you. Thank you for the question. Phil always regarded, and he and I spoke about Bob at some length, as the only younger physicist who he needed to be looking over his shoulder at to make sure he wasn't catching up with him. He had a tremendous amount of respect for Bob. He also felt, Bob was this big, strapping, good-looking guy, and Phil was this, didn't feel he had the movie star good looks, and he didn't have the suaveness either that Bob had, the easy manner, that sort of thing. But he had tremendous respect for his physics ability. And it's interesting that they had this, as you say, this sort of semi-collaboration, not really, because it was at a distance, and it sort of, that relationship remained sort of a wary respect sort of thing, not a whole lot different than with Walter Cohn. I think it broke down when high TC came around, and Bob had his own ideas there, and Phil just didn't respect anybody's ideas that weren't his own. But certainly he generally speaking had tremendous respect for him, and thought it was a tremendous tragedy what happened to Bob.
Well, thank you, Andy, and thank you, Doug, for that question. We'll have many more chances to discuss this, because we're now going to turn to our round table. And before I introduce our distinguished panel, they asked me to say a few words about Phil myself. I just thought I'd give you one very small story about my interaction with Phil. I first learned about Phil as an undergraduate at Cambridge. I was an undergraduate from 1976, which is the year after Phil left Cambridge. But he left behind many legends. And one that appealed was that he had ideas of depth and beauty and great originality. But the other one that went with him was that, which was very worrying, was that he was very hard to understand. So later on, when I became a prospective graduate student, I met Phil at the March meeting in New York in 1980. He took me out to lunch, and he described the Gang of Four paper in the following funny way. He said, well, it's like this. He said, I proved about 30 years ago that, 20 years ago, that electrons are localized in one-dimensional wires. And he said, now imagine if you had a one-dimensional wire that was made of very soft metal, and you pressed it out into a pancake. Well, it turns out that the electrons remain localized. And I was very puzzled by this intuitive remark, which kind of illustrates his love of 1 and 2 dimensions as being very closely connected. Anyway, he thought that I should, before I decided, I should go and talk to some of his current students. So I came up to Princeton, and the first 2 students I talked to confirmed the rumors. In fact, the worst rumors, and they told me they couldn't understand him. They were changing advisors, quitting, and changing fields. And each of them found that he was simply too hard to understand. And so I started to get a bit concerned about this. The third student I met was Jim Sethner, and he closed his door and he said, well, I've got to tell you about this. I go to see him and I hear mysterious and marvelous things, but I usually don't get them. But after a pause, he added, however, he said, what makes it really worthwhile is that sometimes after about 6 months, what Phil was trying to tell me suddenly comes into focus. And those moments of vivid insight make it absolutely worthwhile. They make up for everything. And Jim's words to me, that was it. I was convinced, and I decided to take the plunge. And that began 40 years of friendship I miss him immensely. We all feel a little bit like orphans in our field, which is why we're going to have an interesting discussion now. So let me introduce you to the round table. Unfortunately, I can't individually bring up the faces of each person on the round table, but maybe they can say something very briefly like hello, and that will bring them to the forefront. So let me introduce the now 10 members of our panel. Well, I've introduced one already, that's Andy Zangwell, but he's going to join us today with Premi Chandra, professor at Rutgers University, and she'll moderate today's discussion. We also have Bill Brinkman, who is the former vice president for research at Bell Laboratories, now senior scientist at Princeton University. Bill, are you there? Bill's there, I think. Okay,
he's muted.
Yeah, great. Okay, good. Hide Fukuyama unfortunately can't come today, but Masao Ogata will say a few things that he was going to say. Patrick Lee, professor of MIT and former Bell Lab scientist. Patrick, are you there?
Yep, I'm here.
Yeah, there's Patrick. Okay, great, thank you. Duncan Haldane, who's a professor at Princeton University. He was a co-recipient of the 2016 Nobel Prize in Physics and a student with Phil at Cambridge and at Princeton, and he'll tell us about that later. Ravin Bhatt. Ravin, are you there?
Yeah. Let me start my video.
Okay, great. Ravin is a professor at Princeton University and a former Bell Labs researcher. Daniel Stein.
Hello.
Daniel is a professor at Courant Institute, New York University. Joining us from India in his evening is TV Ramakrishnan.
Hello.
Of the Indian Institute of Science. Thank you, TV, for being here. Ganpathy Bhaskaran, who's a research chair at the Perimeter Institute, but currently in India. And last, Puan Ong, Puan Ong, professor at Princeton University, longtime experimental collaborator with Phil.
Hello.
Puan, yeah. And last but not least, Masao Ogata, who's a professor at the University of Tokyo. Masao.
Yeah, hi.
Hi, great.
Hi.
Okay, so I'm going to now hand over to Premi Chandra, who will explain how we're going to run this discussion. There you go, Premi.
Okay, thank you, Piers, and thank you also, Andy, for a wonderful survey of Phil's marvelous life. Sam has suggested, and I think it's an excellent idea, if those of you who are not on the round table could turn off your videos, then you'll be able to see the roundtable participants better. So please do that. And because of time, we're all awash with reminiscences, but because of time, I will ring the bell when it's time to wind up with each of our speakers, and let's begin. So I'd like to begin with some of my own reminiscences. Phil is a hero to so many of us for his wonderful curiosity, his magical intuition, and his tremendous support of young researchers. As a student, I remember him frequently climbing the stairs enthusiastically to our offices, full of new ideas to share. We would all listen carefully, not understanding very much, trying to act intelligent, but somehow feeling tremendously inspired. I feel very lucky to have enjoyed several decades of such discussions, most recently on the many mysteries of strontium titanate, which, as we heard from Andy, brought him back to his early roots at Bell Labs. Phil particularly liked the fact that when doped, strontium titanate displays unconventional superconductivity and that there are no spin fluctuations in sight. He always joked a lot about that. On a more personal note, Piers and I had dinner with Phil earlier this year. Phil arrived at our table, complete with a bottle of red wine in the compartment of his walker. He was full of his usual gusto, and there was lots of lively discussion across a wide range of topics. I cherish this recent image of Phil, as spirited and animated as ever. We will all miss him terribly, but of course, he will not be forgotten. Okay, my time is up. Now I'd like to turn to my colleagues on the round table. Bill will do this in chronological order, and Bill will start by telling us about some of the golden days at Bell Labs. Bill? Bill?
You have to unmute, Bill.
By the way, to the round table.
How about that? Okay.
There you go.
That's good.
And I'm gonna ask when I ring the bell, and I'll.
Yeah. Okay. I joined Bell Laboratories in 1966, and Phil was there at that time, and I moved into an office that was near his office, where in one corridor, and myself and Bill McMillan and Gene Blount and Phil had regular coffee every morning. I always thought that was a tremendously privileged thing, because the university professors, you see him once a month. I saw him almost every day. And so we had a very nice time there. And we got to the early 70s, and Doug Ostroff and et cetera discovered superfluidity and helium-3. And Bill, at that time, immediately went out and arranged to hire Doug, even though he wasn't nearly finished his PhD. And he called him down to Bell Labs and had him order all the equipment he needed so he could start the experiments as soon as he got there. And so Phil was keenly interested in helium-3 storing. And he and I used to talk a lot, because I was interested in metals in those days. And we would talk about the approach that was taken to explain the spin fluctuation effect in helium-3. After some of the discussions, he wrote up a short paper, and I thought, gee, I better pay attention to this paper and see if it's right, because he had previously written a paper saying that superfluid helium-3 was a D wave material, not a P wave. So I've worked on this for a while, and I finally proved that in fact one of the versions of the order parameter was written by Ballion and Wertheimer, was just not a stable state at all. And I called Phil up to tell him that, and he said, "Well, he's just using the wrong state. So you'd go back to my original paper." Yes, true. It turned out to be true. So Phil was amazing to me that he immediately understood what the problem was. So anyway, he also was always so impressive. All these impressive stories you've been hearing. One of the things I always found about him is every now and then you'd run into him, and you asked him what's new, and he would tell you something radical. For instance, I remember one afternoon I walked in and bumped into him, and he said, "What's happening?" And he said, "Oh, well, I now understand why certain semiconductors, the Berry surface always lies in the middle of the gap." I said, "Really?" "Yes." He says, "Well, you know what he'd done? He'd invented a negative U model, which isn't on a lot of lists here, but it is one of those things that he invented." It was a very important thing that he was able to do that as well. Bill and Joyce at the same time were really very much a center of social activity at Bell Laboratories. And that was always a lot of fun. And we always remember once that we had gotten a summer house on Long Island by the time that this was the late 70s. And we invited Bill and Joyce to come out, visit at our place. And my son, who was only about 6 years old at the time, he was fishing, and he caught a really nice fish, and he put it in a bucket. And Bill goes over to look at it, and somehow or another he lets the fish jump out of the bucket and fall into the lake, the water. So they lost the fish for my son. So forever after that, my son referred to Phil as the man who lost my fish. That he had. And so it was always a bit easy to me that the kids know how to reduce you down to a certain level. Anyway, that's my story. I don't have a lot of other things to add, but Andy has done such a nice job. Thank you very much.
Thank you, Bill. Patrick, you're next. Patrick will continue telling us about the great days at Bell Labs.
Okay, yeah. Well, I arrived at Bell Labs in 1972 as a postdoc. And my background was in atomic physics, optics, quantum optics. So I really didn't know much solid state physics at all. And I tried to teach myself. So going to Bell Labs is really way above my head and also a great opportunity. And I think Bill Brinkman and Bert Halprin were instrumental in bringing me there, at least got me an interview there. When my first project was with Bill, actually. He gave me a problem to calculate the laser threshold of a semiconductor. So I did some calculations and checked, and the result was pretty nice. It agreed, very well with the experiment. And so Bill was happy, and he said, "Well, we should publish this." And so at that time, I discovered that when you do a sum on k momentum space, you turn it into integral. There's a 2 pi cube in the denominator. So I discovered that I had put the 2 pi cube upstairs in the numerator. So I made a 2 pi to the 6th power mistake. And the result was an agreement with the experiment. So it was terrible. So that was my first postdoc experience. And I'm sure Bill was thinking to himself, why the hell do we hire this guy, right? So the other thing I want to relate is that, I was trying to hide my lack of knowledge as best as I can. And the person that really helped me a lot was Morris Rice, because he's the one I can go to his office and, I can confess to him my ignorance and ask him questions. And he always gives me a simple answer and explains everything. So everything I know about solid state physics, I learned from really was Morris Rice's help. So after a few months of this, I was kind of floundering. And there was some kind of excitement in the air suddenly happened. And people were saying, Anderson's coming, Anderson's coming. So that was the time when he was spending his half year at Princeton. And people, all this excitement, and people seemed to feel that, Phil was going to solve all our problems the minute he showed up. Okay. So Phil showed up, and I talked to him, and he actually gave me a problem, which I now learned is maybe not typical. So he gave me a problem because at that time, John Axe was studying, had some data that shows that, he was interested in this ferroelectricity, displacive phase transition. And the data was saying that instead of a soft mode going soft, which Phil was had a role in, it was developing a central peak. And so he took me to take a look at that. And I think he even suggested doing a one-dimensional problem of a double well potential to see. So I didn't know quite what this problem was about. So I just did some numerical simulation.
Duncan, please get ready.
Yeah, didn't get much out of it. And then in hindsight, a few years later, Krum-Hansel and Bishop wrote a very nice paper because the physics is domain wall motion and so on and so forth. So I really missed the boat. So the message is that Phil actually gave me a very good problem, but because of my incompetence or lack of experience, I actually didn't get anywhere with this. So Phil would tell you where to dig for gold, but once you start digging, you are on your own. You swim or sink, you're on your own. So that was my experience. Now, fortunately, towards the end of the first year, I benefited from another mistake. But this time not made by me, but by somebody else. It was Alan Heger was claiming that there was a huge superconductivity fluctuation in TTF, TCNQ. And so that got me into charge density wave and led to this paper by Lee, Rice, and Anderson. And I think that really, I kind of redeemed myself and launched my career. So I guess if there's a message for younger people out there, is to say that don't be too harsh on yourself. You can make mistakes, and you hang in there. Something good probably will happen. It happened to me. I was lucky. So that was the beginning of my interaction with Phil. And over the years, I must say that my wife and I, really enjoyed. They extended the hands of friendship to us, even though we were much younger. And in particular, we remember visiting them in Cornwall in their house. And there, Phil was really totally relaxed, and I can see the interaction and love between him and Joyce. And they would break out in songs of, Tom Rare songs, and that was really marvelous to behold. And in later years, as many of you know, unfortunately, Joyce had a stroke about 10 years ago. But Phil was really by her side all the time, and he was really dedicated to her. I'm not sure how much Joyce can communicate with the rest of us, but they seem to continue to be able to communicate. And watching them, I think Phil would go and read for her for an hour every day. And just watching the interaction was very moving and very touching for me. So that's my remembrance.
Thank you, Patrick. And now we'll hear a little bit about what it's like to be a student of Phil. So Duncan.
Okay, I'm probably his second or third student at Cambridge, and I first met him and he gave a class which he co-taught with Mike Green, the string theory founder. Phil taught half the class and Mike taught the other half on advanced quantum mechanics. And I decided to stay on at Cambridge, and I had the choice of working with either of the two. And luckily, Phil's a very simple way of coming up with simple models for physical things in condensed matter made me feel it was a much more a concrete problem than the kind of abstract string theory type problems. And so I was lucky I made the right decision of which person to work for, because string theory died out just after that for a long time. But what I found about Phil was this this conceptual simplicity of coming up with simple models. Before that, physics had seemed to me an exercise in the rotation group, working out Clebsch-Gordon coefficients and spherical harmonics. And of course, he threw all that kind of stuff away and came out with very simple things which sound attractive. And for example, I was very impressed in the first semester when I was there that, I want to share my screen and it can't be shared. Hello? I want to share my screen. Okay, you can't share it. So basically,
you can share it now, Duncan. You can go ahead.
To share my screen.
You can do it now.
Okay. Oops, wrong screen. Okay, this one. Yeah. So the simple picture he had of metals and superconductors and magnets, basically saying that you turn on the Coulomb interaction and get a kind of Anderson model with localized orbitals, and you get magnetism with one electron, single electrons in a site, and you try to you form bonds for superconductors. And he had an approach that showed you why you couldn't get high TC superconductivity, because if you tried to make the bonding of the pairs too strong, you would get a covalent insulator, which was just a localized form of superconductivity. Well, very simple ideas, but I was very impressed by such basically easy ideas. And the models, let's see if I can get back to can I unshare now? Yeah, stop share.
No, we never saw your screen, Duncan.
Oh, okay, I'm sorry. It didn't seem to work then. Okay. You can see me, right?
Yes.
Yes, I can see you.
Okay.
Yes.
Okay, so when I going to talk with Phil, so he gave me a problem at first, which was related to the renormalization group, which he just done the work with Yuval.
Robin, you're next.
Okay, and basically going to see Phil, I'd go to talk about my problem, and of course he wouldn't really talk about it at all. He'd tell me what he was thinking about that day. But I found that was a tremendous education, because I would get to basically watch Phil thinking about things and reducing everything to very simple models. And that's what the toy model approach is, what I really learned from him. And I think at that time, not many people were pushing toy models. The other people in Cambridge were all doing band structure theories and ab initio calculations to be very accurate about everything. And it was really a breath of fresh air to realize you had to throw all the details away and work with very simple models.
Okay, thank you, Duncan. Ravin?
Yeah, I'm ready.
Yes.
Okay. My first encounter with Phil was in January 1976, when as a 23-year-old, I interviewed at Bell Labs. My advisor, Bill McMillan, had been a protege of Phil at Bell Labs, and he had extolled Phil's deep and thoughtful approach to physics in the prior months. So I arrived at Bell full of trepidation at meeting this giant. What I didn't know at that time was that Phil was always open to fresh ideas and friendly to young budding physicists. He saw them as potential recruits to his way of thinking. He was also very protective of his proteges, so I had that advantage in having Bill as an advisor. Much to my amazement, Phil invited me for dinner at his home in New Vernon and personally drove me there during my interview talk. This was the first of what was to become many home-cooked meals made by Joyce and later by my wife Swati that we shared at our homes over the years. But back to January 1976. I had no idea of Phil's driving style. Having just spent the several years in the rectangular grid of streets in the flatlands of Urbana-Champaign, the daredevil driving that Phil subjected me to through the windy and steep roads of the Watchung Mountains took me by complete surprise. But I survived, though I confess that when I found out that Mike Cross was going to drive me back to my hotel, I was relieved. It was some years later that I learned that Phil and Elihu Abrahams had a friendly competition as to who could drive in less time between Princeton and Bell, each racing down newly discovered and windier country roads, avoiding traffic lights at all cost. A year after my interview, after I joined Bell, Phil invited me to participate in a two-month-long joint US-Soviet workshop in summer 1977 at the Aspen Center for Physics. That opportunity led to a 40+ year affiliation with the Aspen Center for me. And this is just one of the many things for which I'm very grateful to Phil. In fact, the Aspen Center was also the venue for a winter workshop that Juan Ong and I organized in the celebration of Phil's 75th in January 2000 at the turn of the century. The workshop covered forefront topics in condensed matter physics, and most of them emerged from Phil's enormous contributions to the field during the past 50 years. For the proceedings, we took the title "More is Different," stealing it from Phil's famous article of 30 years ago. We felt that this 3-word phrase aptly summarized Phil's point of view about physics and science in general. A decade later, at the 50th anniversary of the Aspen Center, I had the opportunity of interviewing Phil, and a recording of that is available. Needless to say, Phil's brand of physics has strongly influenced most of my physics career. The 2 citations for his Nobel Prize, Anderson localization and local moments, played a big role in my foray into doped semiconductors. Valence bond formation was at the heart of RVB, but it was also at the heart of the disordered version that I worked on with Patrick Lee, the valence bond class, which is more commonly known as the random siglet phase. The seminal paper by Edwards and Anderson inspired me to work on spin glasses for over a decade. I'd like to come to Phil as a person. While he was extremely selective in approving the physics of his colleagues, he was completely non-discriminatory when it came to the country or background of his colleagues. His collaborators and proteges hailed not just from the US and Europe, but also from Japan, Turkey, India, and China. Just look at today's panelists. The background of 2/3 is South or East Asia. For someone of Phil's generation, born and raised in the Midwest, to have this color blindness, as I call it, was truly unusual. This, along with Phil's unique physics, sums him up for me in 3 simple words. Phil is different. I'd like to now share a few photographs of Phil at the end.
Dan, you're next.
Can I share screen, please?
I think Robin wants to share his photographs.
No, that's fine. But what I meant was get ready. You're not saying anything yet.
I'm ready.
I just want you to unmute.
Are you able to see my?
I don't see anything.
Not yet, no.
Screen sharing, it says.
Oh, Dan, I just asked you to unmute to get ready.
We have a white screen, Robin.
Yeah,
there you go. Got it.
Do you get it now?
Yes.
Yes.
Okay,
Yes.
so let me just go back. Okay, so this is the first photograph I have, which is this conference that Juan and I organized in honor of Phil, which is in the center, and Juan and me and Duncan, David Pines, Steve Ramakrishnan, Miriam Sarachik, and Elihu Abrahams, and a whole host of Phil's admirers and participants at this conference. More is different. Let's see, how do I? Oh, for some reason, I'm not able to move the. Oh, maybe this is the way to do it. Yep, there we go. So in 1998, this is at our home. Phil describing to the 2 new Nobel laureates, Dan Sui and Horst Stormer. We had several festive occasions at Princeton with Nobel Prizes. This is one of them. Again, another time when Dan and Phil were visiting, and Phil again, always expounding, and the rest of us listening to the interesting things he had to say. And this is my last photograph of Phil, which is 2 days after Jim Peebles won the 2019 Nobel Prize. It's dated October 10th, 2019. And that's it.
Thank you very much, Robin. And now Dan will talk about the student experience at Princeton.
Okay, well, thank you very much, Priyami. And I also wanted to thank Andy for a really, really nice talk. It really brought back a lot of memories and it was a lot of fun. So I'm going to talk about Phil at Princeton in the late 70s, early 80s. I arrived at Princeton at the same year as Phil in 1975. And in the summer of 1977, I asked Phil if I could work with him, and he was very obliging. He said yes. And 2 months later, he won the Nobel Prize, which was a little overwhelming for beginning graduate students, and what it meant, and what other graduate students were happy to tell me what it meant. They told me it meant that I would never see Phil again. But as it turned out, that was completely wrong. In fact, I would say that made almost no difference whatsoever in Phil's availability, aside from a few minor trips he had to take that spring, that winter, like Stockholm. Other than that, he was always there or available by communication one way or another. So it has been said by peers mentioned that what Jim Sethna said, and Duncan alluded to it too. Phil's nickname back in those days, so then again, we're talking about 77, 78. His nickname at that time, a lot of people referred to him as the Delphic Oracle, because there were a lot of similarities, right? When you went to the Delphic Oracle, she would see the future, but she would speak in riddles that would make it very difficult for an ordinary mortal to understand. But I was going to Jim's Pierre's recollection of what Jim Sethna said was pretty much exactly what I was going to say. It's pretty much the same thing. When my recollection of talking to Phil is that it was mostly free association. Phil would simply talk about things, as Duncan said, that he was interested in that day. And a lot of times you would think it did not relate to what you had gone to talk to him about. But in fact, as Jim Sethna had mentioned to peers, sometime later, all of a sudden it would hit you. You would understand what he was talking about, or at least have a better idea. And you'd realize that he had mentioned something very profound that it would do you a lot of good to think a lot harder about. You know, Phil was not the type to give, at least with me, he didn't give a problem, say, go, you know, here's a problem, work on this or work on that. He would say, I think maybe you should think about this, or maybe you should take a look at that paper or that experiment and tell me what you think. But he was always available, and the discussions with him were always worth much more than I could ever say. So back in the late 70s, the problems that were in Phil's mind, there was a lot going on in condensed matter at that time, a huge spectrum of problems. But Phil, I noticed, was very much focused. He was still very focused on the Kondo problem, which he had worked on a few years earlier in the early 70s. He was very much into disordered systems, particularly amorphous semiconductors and glasses. Oh, okay, spin glasses, the TAP paper had just come out.
But not yet. No,
Oh,
not.
okay, I don't think I've only, yeah, okay. I have another couple of minutes.
You have another
Okay.
couple of minutes, but I just
Thank
wanted to tell Rama to unmute.
Oh, okay, thank you, Praveen.
Well, I'm not gonna cut you off.
and-
I just wanted to give you a sense of where we are with time, because we can
Okay.
we all are full of reminiscences, and so.
All right, 2 more minutes, 2 more
Yeah,
minutes.
that's
Okay. Okay, so in 78, 79, the Gang of Four paper came out, which returned his attention in a big way to localization and correlated electrons, and Rama will be talking about that. One of the things, though, I do want to mention is that one thing that Phil never talked about, or very little, was the renormalization group and calculating critical exponents, which I remember back in those days, a lot of graduate students, condensed matter, were working on. He just was interested in things that were not necessarily what people in the mainstream were interested in. Although when Phil was interested in something, it would become mainstream sooner or later. Phil he was a wonderful human being. He treated his students like family, and he had a very impish sense of humor. When I got engaged, he threw my wife and I an engagement party at his home, and he gave us as a gift from the old rhyme, something old, something new, something borrowed, something blue. The something old he gave us was an old shoe of his, which I think we still have, but that was Phil. Just one last thing that I want to say, and that is, there was some talk about Phil's political fights. Phil did get into political fights, particularly he was very involved with the SSC, which caused a lot of hard feelings in the high energy community. I myself got into fights with people in the high energy community over this, sort of defending Phil and Phil's viewpoint. But I will say that to me, that is sort of minor, because Phil, I think, was the greatest unifier intellectually of his lifetime. He early on saw broken symmetry as a bridge between condensed matter and particle physics. The More is Different paper completely changed the way that I think we all thought about science as an interconnected web of equally fundamental problems rather than a hierarchical top-down kind of structure. And believe back in the early 70s, for those of us who were around at that time, this was not the way people were thinking back then. People were many people were strict reductionists. And I think quite a few may remain that way today, although it's become less, maybe less popular to actually admit that. But Phil really gave us a way to think about science, not just condensed matter. Of course, Phil was the founder of modern condensed matter physics, and he has been its greatest influence on condensed matter physics, not only during his lifetime, but I think for decades to come. But what Phil really impressed upon us was something that went a lot deeper than that. And I only have like 30 seconds, so I guess all I could really have time to say is that the boundaries between scientific disciplines, whether it's condensed matter versus high energy or physics versus chemistry or whatever, those boundaries are put there by us. They are not put there by nature. Nature doesn't recognize any of this. Nature just sees a unified whole of physical and biological phenomena. The More is Different paper, I do think, caused a tremendous shift in the way all of us think about science. it made a huge influence in my own life and scientific thinking. And more than that, I think it is now recognized, I think, and as it should be, when I gave an interview with somebody when Phil died about Phil, and I mentioned that I thought of the Moore's different papers as sort of Magna Carta for the Santa Fe Institute and all of the complexity institutes in research and complexity. That is now another branch of science that I think without Phil would look very different than it does now. So I think Phil's contributions go so far outside of condensed matter physics. I think he has made tremendous contributions to science as a whole.
Thank you, Daniel. Rama?
Yes, can you hear me?
Yes.
Okay, well, first I want to thank you and peers and other motive forces of this roundtable and get together for inviting me to participate. Well, I should start perhaps from the beginning. One of the first times I heard about Phil was when I went for an annual physics meeting in the West Coast I think it was 1969 or so. The meeting was very interesting. But the more interesting thing was that there was a question of, it was an annual meeting. So the question was, what do you do next year? Then someone said, well, whatever Phil Anderson is interested in. And that did happen. The first time I saw him was in Toronto at a conference on magnetism in metals in 1976. I had actually been able to put together enough money to somehow get there. I talked about what we had been doing on spin fluctuations in weakly and weakly ferromagnetic and almost ferromagnetic metals. He sat in the back and heard me, and then we met. And I was surprised to meet him because he was not very prepossessing as the physicists whom I had met in Columbia or La Jolla were, but he had twinkling and kind eyes. A year later, I landed up in Princeton, and the first few weeks of encounter with Phil were very disheartening for me. I listened to him. I couldn't understand him. And I was a rusty physicist who was rather low on self-confidence. After a few weeks of this, I felt I couldn't take it anymore. And I went up to Columbia to meet Quinn Luttinger, my PhD mentor, to complain to him that I was in a very sad state. He heard me patiently and finally said, well, Phil doesn't get things out beyond a certain point of clarity, but he is the most talented person in our field. And that was that. So I could take it or leave. I would like to add two comments to this comment. One is that Quinn Luttinger and Phil Anderson knew each other for a very long time. They were graduate students at about the same time, one in MIT and the other in Harvard. They were perhaps at the opposite extremes in their practice of physics, but they had a tremendous respect for each other. Phil actually was one of the authors of the obituary for Quinn Luttinger, along with Walter, Phil along with Walter Cohn was one of the authors of the obituary for Luttinger in Physics Today. And he remarked there on the gem-like clarity of many of Luttinger's papers. Once Phil told me that when he had done his work on localization, he discussed it with Walter Cohn and Quinn Luttinger. And Walter said, this is wrong. Quinn said, yes, of course, this is right. And Phil felt that, well, if two of the physicists, condensed matter physicists whom he respected most, felt so differently, then there must be something there. actually, the fact that Phil was not easy to understand has already been mentioned. It's well known, and perhaps it was very common in that time. But later, I began to understand the association of ideas which went through his head, understand a little bit, and that somehow made it much more interesting and worthwhile to listen to almost anything which Phil had to say on almost anything. I must talk a little bit about the scaling theory of localization and how it came about. Phil had come back from Lezoux summer school and was talking in a course he was giving at Princeton on on electrons in metals. And he talked about the fact that, well, what was it? The back of his mind was that Thouless had some idea of how the conductance was a response of the system to of a disordered system to some perturbation at the end. And so this would imply conductance in a finite system, and therefore this conductance ought to change as a function of the scale size, and we know what the conductance would be at opposite extremes, and since it's a finite system, the scaling curve ought to be smooth, and he drew it. Then I felt that maybe for large values of the conductance, one could actually do something, and it turned out that one could. And as Andy said, and in answer to a question, this work was called the Gang of Four, after the famous four people, including Mao Zedong's wife, who were, I thought, supposed to be running the state during his last years. The last time I met Phil was at his 90th birthday international conference, and it was quite amazing because Phil was not only there all the time and asked questions, was in the front row, but it was a meeting of 3 generations of physicists in the same field. People who started life with him and people who were going to start their life after him. Thank you very much.
Thank you, Rama. Ganapati?
Yes,
Please.
I am there.
Yeah.
Thank you, Premi. Thank you, Piers. Thank you, all the friends. And hello to everybody for this wonderful occasion. I'm going to start with a picture and share 2 slides.
Could you speak a little louder, Ganapati?
Yeah. Do you hear me now?
Yes, that's better. Thank you.
Okay, I will. So this is the picture of Anderson. His window overlooks the roof garden at Princeton. And so it's a very nice picture. So I'm going to tell about how Phil changed my career. So it's going to be very personal. So it was in ICTP Trieste. Thanks to Area Tosati, I spoke to Phil for a long time. Phil was in a semi-sleepy state. It was a monologue. Occasionally, he made some remarks. When I described to him my work on supersolid helium-4, he woke up. He disagreed with me and said, supersolid helium-4 does not exist. We parted. Then I joined Phil's group as a visiting research staff next August 1984. 9 years after my PhD, and happily unsettled, Bangalore, Madras, Trieste, and Princeton. Princeton was great and exciting, wonderful colleagues and so on. Phil and I discussed a variety of topics on a daily basis, spin glasses to consciousness. It was 3 years of wonderful and exciting stay. I will describe an incident which says that how I felt that I was wanted. In mid-86, there were some glitches in renewal of my US visa. News reached Anderson. He said, I will call George Shultz and fix it up. George Shultz was a Secretary of States of USA. Phil knew the Princetonian personally. I felt elated, but politely stopped Anderson from calling Shultz. The problem sorted itself out and prepared me for something exciting. Instead of Secretary of State solving the problem, Secretary of Princeton solved the problem. Early November 1986, Phil walks into my office and places a paper on my table and says we should work on it. It was Bednarz-Muller's famous paper. I got excited and worked for a week and presented a theory to Phil. He patiently listened and said, "Your theory is beautiful, but totally irrelevant for Cupriate superconductivity." I pursued my theory passionately and wondered if Phil is losing his grips on superconductivity. Few weeks later, in mid-December 86, Phil was to go on a long trip to India for a conference. Before leaving, he essentially said, "Bhaskaran, your theory ignores spin-half Mott physics, even though you drew my attention that lanthanum copper oxide is a Mott insulator." His remark did make some subconscious rumblings in my mind, but I continued to ignore Mott physics and worked hard. Moreover, Phil had no theory till then. I waited for Anderson's return to Caltech from India, called him over phone to report progress on my front. Before I began, he shut me up. He said, "I saw the light in my trip to Bangalore," and uttered 3 cryptic sentences. I began to see the light and said, "I understand what you are saying and will call you soon." I put down my phone abruptly. After 15 minutes, I called Phil and elaborated based on my understanding of his 3 sentences, his novel solution to Cupriate superconductivity. Phil remarked happily, "You have smelled it right." That happy resonance started our long collaboration on RBB theory of high tissue superconductivity. Fast forward 31 years. This is Phil on his 95th birthday at Princeton. So this is 13th December 2018. So this is my last slide. After visiting Princeton for a week, I was about to leave for Perimeter. At the end of our long discussion on cuprates, supersolids, Phil remarked, "Bhaskaran, you and I understand
empathy.
the
We
can
only see the original slide. At least that's what I'm
Sorry?
seeing.
You can't see my...
We only see the first slide you showed.
Oh God.
The roof garden. The roof garden. Yes.
You don't see this. Oh, I'm very sorry.
Yeah.
Okay, it's too late. So I will read this.
We don't see the one from the 95th birthday.
Oh, you don't see that picture also?
We only see the roof garden, which is very nice.
Oh, I see.
Okay, but keep on going.
I will, yeah. My son is trying to help me. Okay, I will, since I'm taking others' time, I will just rather go. So this is the last one. I said, after visiting Princeton for a week, I was about to leave for Perimeter. At the end of our long discussion on cuprates, supersolids, etc., Phil remarked, "Bhaskaran, you and I understand the theory and mechanism of cuprate superconductivity so well. I wonder why others don't understand us." We had our last laugh and I bid goodbye. So there are some nice pictures which I wanted to show, but it's not coming up. Do you see this picture?
Go to full screen. Go to slideshow.
Go to slideshow. Okay.
Bottom right hand.
Yeah, there. Now we can see other pictures.
Now we can see. Yes.
Yes. Now where would you? That must be his 95th birthday.
Do you see it now?
Yes. Lift it up a bit. Lift it up a bit.
Make it a little larger. Yeah.
Yeah. This is Phil Anderson and me on his 95th birthday. Thanks to Shivaji Sondhi, I told him that it's his birthday, so we arranged for a beautiful cake party. We had wonderful time and discussion. Then this is after the party, Phil, Duncan Haldane, Shivaji Sondhi, Daniel Stein, Elliot Lee, Ravin Budd, and several other friends. Then this is Ravin, Phil, and Duncan the same day.
We don't see the next one. You have to go down. We don't see the one the next day.
Do you see this? Do you see this?
We see the large group picture.
Okay.
Yeah, I think
do you see
your
the
PowerPoint screen?
What do you see?
We see your PowerPoint application. So if you just scroll in the PowerPoint application rather than in the screen that you have put on full screen, maybe do you have 2 screens by any chance?
Okay, probably you see it.
That's very. That's
now you advanced it.
Yes, with Robin and Duncan. Oh, that's nice.
That's nice. This is Ravin and Duncan. And
I think if
Duncan,
you scroll down the thumbnails, that will work.
You don't see it?
No, we do. So scroll down. If you scroll down on the left-hand side, we'll be able to see it.
Okay. So now then this is with a student.
No, we don't see.
Undergraduates.
We're with,
oh,
well, we're with Robin and Duncan.
okay, sorry.
Do you want to scroll down on the left-hand side? Yeah, now.
So this is, oh, sorry, it's small, but this is Duncan, Phil and me, and then it's a student, and with another girl student, so on, so, and this is with Herio and
yeah, that's
Phil when they visited. Okay, so that's what I wanted to share.
Okay, thank you so much, Ganapati.
So this is what I wanted to say, the last one, because my parting, you know, as they say, parting shot, we laughed because he said, Bhaskar, you and I understand the theory of and mechanism of Q-plate superconductivity so well. I wonder why others don't understand us. We had our last laugh. Thank you.
Thank you so much, Ganapati.
So Phil.
Yes. Oh, hello, Susan.
I just dropped in to say hi. I'm out again.
Okay, thank you. Masao, please give us the Japanese perspective, please.
Ponong is next.
Oh, sorry. Juan.
Ponong is next.
Sorry, Juan, please.
Hello.
Sorry about that, Juan. Apologies.
So most of what I wanted to say have been said. I first met Phil in '85 when I arrived on campus as actually it was my interview trip to Princeton. And Phil and Joyce were very kind to take me and my wife out to lunch. We had lunch in their borrowed apartment here in Princeton. And it was a terrifying experience, especially for my wife. I just married her the year before and was trying to persuade her to move across the country from LA. And but they were very nice. They hosted us for lunch. And then in the middle of lunch, George piped up and said, I don't know why you would even think of coming to Princeton. There's nothing here. And that confused my wife quite a bit, but that was the character of, I soon learned a few years later of both Joyce and Phil, that they were completely disrespectful of pomposity and hierarchy and so on and so forth, even though they were probably the most prominent citizens in the town at the time. Then the year later, high TC broke. So there was a very fortunate timing. So I had something to work on. I had lost my NSF funding when I moved to Princeton. And having high TC to work on was a godsend. And so that started a very long collaboration in which I witnessed how Phil thought about ideas of, this was probably the most challenging problem that he worked on, and but he refused to surrender. I mean, he brought everything that he knew to the table, and he made a lot of progress. So I think one of the techniques was this notion of fractionalizing the electron into spin-ons and holons, which at that time seemed very bizarre and turned vast fractions of the community off. This could be his most important lasting legacy, I think. This notion of spin-ons to describe neutral fermions, especially in highly entangled, strongly correlated states. I think this is now a very active area of research. So to the young folks out there, if you're looking for a very difficult problem, both as an experimentalist and a theorist, I think the time is right. I think spin liquids will be the place to work on. And we owe this completely to Phil, right? He started the field of spin liquids back in the early 70s with this very puzzling paper on spin liquids, and then dropped it, and then high TC came along and he brushed off the dust and reintroduced the ideas of spin-ons and hole-ons. But now I think with modern technology, modern discoveries in material science, the field is, I think, is prime for major discoveries. And it kind of saddens me that he left us just a little bit too soon, right? If his death had been delayed by 5 more years, I think this would be yet a very big feather in his rather crowded cap. So I want to leave you with one perhaps less physicsy thought. Phil was a self-professed curmudgeon. I mean, he recognized that his very pithy way of communicating thoughts and his tendency not to suffer fools gladly made him a rather formidable guy to talk to if you don't know him. But he was at heart a kind of shy and very warm personality. And he had a very strange sense of humor. So most people, when they want to crack a joke, they are delighted to share it with many people. But Phil kept this joke to himself for decades. He enjoys would throw these lavish dinner parties, right? Maybe involving 15 people. And at the end of this lavish dinner, Phil would go around and ceremoniously poll everyone, decaf or non-decaf. So he's going to make coffee, right? And then he would hold up both hands with the numbers of decaf and caf and march into the kitchen. And then he would make just one pot of coffee with the correct fractions. And this was a well-hidden secret. And everyone was very puzzled why they always felt that the coffee was definitely had caffeine in it. It wasn't until Joy spilled the beans, so to speak. She said, oh, it doesn't matter. It doesn't matter which cup you take because they're both the same. Phil just mixed them all up together. And we wouldn't have known this prank that he was pulling on us until Joyce let out the secret. But this is an example of his very puckish sense of humor. Thank you. Wonderful panel.
Thank you so much, Juan. This was Phil's mean field approach to coffee.
Yes, exactly.
Wonderful. Masao, would you continue and tell us about Phil from the Japanese perspective, please?
Yeah, okay. So first of all, thank you very much for Chandra and PS and inviting us. And unfortunately, Hide actually sent an email 1 hour ago, and he said he will go to the bed. So.
Yes. Masao, thank you so much. I know it's the middle of the night for you. Thank you so much for coming to us in the middle of your night.
No problem for me, but for Hide, maybe it's a little hard too.
Yes.
And maybe first, maybe I should share the Hide's.
Yes.
Yeah. So shall I?
Can you share the screen?
Yeah, I've been trying this one. Okay. Does this go well or
yes,
still
not? Thank you.
It's now on?
Yes, we can see.
So this is I mean, he does a PDF file. So that is, I think he wanted to show. Okay, so let me, so first thing is, okay. Can you see the picture now?
Yes, thank you.
Okay, so this is the same as Andy showed. This is a kind of Japanese plant, and unfortunately it died just when the field passed away. Yeah, that is a thing, first thing. And second thing, maybe he wanted to show is this one. Can you see this one is this
yes.
is the 60th birthday symposium in the fields held in 1983.
Maybe you can scroll it down because we.
Yeah.
Yes, that's very nice. Yes, yeah, I remember that. Yes.
Now, yeah. So this is, I think Hide attended this one. So he had photos at that time. And Hide said that maybe the Bill Brinkman, Bill has a chair or something like that, but I'm not sure. And so Hide wanted to say that at maybe this part. Can you see the so at the end of the in the conference, Phil made a comment on Kubo, and he said that Phil said that I was shocked when the Kubo said he had found me because I had found him. That is yeah. So Hide was wondering what is the first occasion when the Professor Kubo and Phil met. So he was wondering because this is what Phil said is that it's very delicate occasion when they meet somewhere, and maybe at that time the anti-phenomenologism or something like that. But this is a kind of interesting history, and that is what Hide wanted to say. And these are the pictures at that time. Yeah. Okay, so he has many things. So let's go to the third one. That is a Katsura tree.
Could you scroll down a little bit, please? Yes, thank you.
Yeah. Okay, so this is a tree which Phil came to University of Tokyo in 2002, like this, and he gets the honor of doctoring degree from the Tokyo University. So at that time, he made this kind of plant. And yeah, that is still, this is in ISSP. And it is very, still very, you can see at the ISSP. So at that time, this is a field, and this is a Hide Fukuyama. And actually, I was also joining there.
Oh, that's nice.
Okay. So the fourth part, I think at that time, after that, we went to Hakone with Phil and Hide and some other colleagues. And that is one of the pictures which Phil enjoyed some kind of, so as Naipan said, that Phil has such kind of humor. And he just jumped on this kind of towing machine in which we happen to see. So that is what Hide wanted to show. Is that fine?
That's great.
Yeah. So let me. So So this is a part of the Hide's part. So shall we start my part?
Yes, I'll start now. Yeah.
Okay, maybe I have some extra time. So next thing is my part. Okay, I will try to share some another picture. Did it start?
Yes.
Yes, we can see. Thank you.
Okay, so this is a, okay, well, wait a minute. Actually, okay, I was actually postdoc in field from October 1991 to March 1993. So this is a picture which I took maybe the last time when I leave Princeton. So this is a picture of 1993. This is of course in front of the field's office in the third floor of Jadwin Hall. So this is me, and yeah, this looks young. And yeah, at that time, I mean, when I was postdoc, almost every day, Phil and Naipan and I went to lunch together almost every day. So actually, at that time, Naipan always brought some new experiments about high TC or various many other things, and explain the latest interesting experiments to Phil. And Phil made every time sharp comments on that, every kind of experiments. So I was just listening to them, but it was, for me, it was great experiences. And actually, one day after lunch, I went to Phil's office without appointment. And at that time, Phil sat in front of a computer, and on the screen, on the computer screen, there was a square lattice of solid circles and open circles, just like a spin model simulation. So, for example, like a Ising model, or maybe it can be a TJ model. But so I thought I was rather surprised that Phil can make a numerical simulation by himself. So I asked what kind of simulation it is, but Phil was very upset and tried to hide the screen from me. So, so as you can guess, that screen on the screen, he was playing the game of Go. So maybe he was playing the Go game of Go on online at that time. So this was he was very upset to be found to playing the Go in the computer. So this was a single occasion when I saw Phil was completely upset. So this is a kind of a picture which Phil was playing a Go in some Japanese conference. Yeah. Okay. So this is also the same picture, but this is me. Phil is playing Go here. Yeah. So this kind of, there are many Japanese colleagues that are doing the game of Go. So Phil actually likes it. So maybe the last part. So this is one of my best shot of Phil. This is as you can guess, this is in Aspen Center for Physics, probably in 90s. Yeah. Yeah. So, but as many other persons said that Hide is very serious about physics and also sometimes very aggressive. And I had several chances to stay in Aspen Center for Physics with Phil. And I remember that one afternoon, Phil and maybe the Ted Gibor, they were sitting on a table in the garden of this Aspen Center, and they seemed to discuss quietly various kinds of physics. So all that afternoon, so they looks very happy. So yeah, so that is a kind of a memory. I have a very good memories with Phil, such kind of things. And I actually learned various things from Phil. Of course, it is very hard to understand what he's trying to say, but I learned many things. In particular, I learned from him that some very serious attitude to physics. He's always very serious, and so that was for me it was very good experiences. So I miss Phil very much. Yeah, thank you very much.
Thank you very much, Masao. Andy, would you like to round up our roundtable? Andy?
Sorry, here I am.
Yes.
I had more time than anyone else, but
we can't hear you.
Yeah, we cannot hear.
Yeah, we can't hear.
Now.
And Andy, we can't hear.
He seems to be frozen.
He's lost his connection.
He's lost his connection. Yeah.
Okay.
Maybe we can go to the more general discussion, and Andy can join us when he gets the chance.
Okay. All right. So first of all, so hopefully Andy will join us.
Wait, I'm back. Can you hear me now?
Yeah, unfortunately we couldn't hear you.
Okay. Yeah, my internet crashed.
Okay, sorry about that.
I'm
Okay.
I'm back. I'm back.
Welcome
I just
back.
want to make two brief comments. One with regard to Robin's comment about Phil's driving. I had the opportunity to interview Leo Kadanoff shortly before he died, and I asked him about Phil. He had quite a bit to say, but the very first thing he said was when he first met him, Phil took him driving in the French Alps, and Leo's never forgotten it because he was shocked that he actually got away with his life, given the nature of Phil's driving. I also wanted to follow up a bit on Masao's comment about he walks in on Phil playing Go on the computer, but he said that his thought was, well, maybe Phil was doing a simulation. Phil would never do a simulation, and in fact, he had a well-known attitude about computers. He hated them.
Yeah.
A long way, but it's interesting because, well, okay, how does it express itself? For example, in 1970, former postdoc of his, Marvin Cohen, published the first pseudopotential calculation of the charge density of silicon, and he sent this preprint around. Marvin did, and he sent it in particular to Phil, who he was very close to, and Phil immediately prepared a comment saying that all of Cohen's results were wrong. He had everything. The bond charge was wrong, and this was wrong, and that was wrong, and he had intuition about this because his very first PhD student ever, who was at Cambridge, actually did an electronic structure calculation, not well known, a one-body calculation, and so he had a little bit of experience with this. But of course, Marvin had much more experience with this, and they had so Phil took his comment and he sent it to Marvin before he sent it back to PhysRev Letters, and asked Marvin for his comment. And what Marvin told me was that he pleaded with Phil that he really did know what he was doing with these computer calculations. He wasn't just turning the crank. They had thought about it carefully and understood it. And he basically said that, Phil, you need to not publish this, not for my sake, but for yours. And in fact, this succeeded in convincing Phil. He did not send the comment in, and very soon it was confirmed that Cohen's calculations were quantitatively correct. They agree with X-ray scattering measurements of the charge density. Nevertheless, Phil remained pretty hostile to computer calculations, and he wrote a famous article which was commissioned by the French journal La Recherche, and it was called The Great Solid State Dream Machine, which he circulated. He wrote it in English, and it was circulated to many people, in which he worries that computational physicists will eventually squeeze out creative non-computational physicists, and he worried a lot about this. And in fact, the La Recherche took the article, translated it into French, and published it. It never appeared anywhere in English. Now, this is interesting because he had a great deal of respect for certain people like Bill McMillan and his ability with computers and numerical work. And so it was a bit of what he didn't like, actually, was electronic structure calculations. And he had a long running, low simmering conversation with Walter Cohn about this, even though Walter himself, of course, never did any calculations using his own method. But I wondered at the end of his life, did Phil, after all the numerical work which has been done in connection with the Hubbard model and other problems which can only be attacked in the weak or strong coupling limits, and then the world seems to live in the middle, and only numerically does it seem we can get at them. And I asked him quite recently, had he mellowed a little bit with respect to computer work, and that it really did seem to have value in understanding what was going on. And he closed his eyes and he thought for a while, and he said, nah. So I think I'll stop there.
Thank you, Andy. I'd like to, first of all, I'd like to thank all of our roundtable participants for this wonderful set of quintessential reminiscences about Phil. And now, in the brief time we have available, I'd like to open up the discussion to the participants. Ollie, I believe you wanted to say something about Phil. Are you there? Ollie?
Yeah, I'm.
Yeah, will you say something? I believe you wanted to say something. Would you like
Yeah,
comment,
I'd like to say a few things about Phil's work in neutron star astrophysics.
Can you turn on the light? Because there isn't that much
Yes,
light.
that's what I got up to do. Just a moment.
Thank you. Okay, thanks. Now we can, yes, better.
Right. So I joined. Can you hear me?
Yes. Yes, we can.
Yes.
Okay.
Unfortunately, we have to have a quintessential thing, so not too long.
Yes, yes. So I leave the personal things out then. No anecdotes. What Phil did in neutron star astrophysics is a seminal paper in 1975 in Nature with Naoki Ito. That paper starts on analogies with experiments in type 2 hard superconductors and how the magnetic field evolves in a rather jittery fashion. And also there were at that time a bunch of experiments in rotating helium-2, which also showed sort of discrete sudden steps in the rotation rate of the container holding the helium. And motivated by those, Phil took this analogy to neutron stars, which had been discovered, as you know, in 1968 by Justin Bell. And then immediately, the most observed, most interesting youngish pulsars, the Crab and Vela pulsars, showed what are called glitches, sudden spin-ups, which then relaxed in rather complicated ways. So that was a problem to explain these. And Phil's analogy was that the vorticity in the neutron star, superfluid, neutron superfluid inside neutron star, would be held constrained by pinning sites. So its angular momentum transport, which had to expel the vortices in some mean radially outward current, was not smooth. And that, in this first paper, he noted that he put the idea of vortex creep in analogy with flux creep in superconductors, and both noise and small events, small glitches, as well as the rarer, discrete, large glitches could be explained in terms of vortices moving in a constrained medium with pinning. And that brings, sort of enlarges into astrophysics what happens for the angular momentum or momentum transfer in a superfluid, replacing the classical Navier-Stokes equation for classical fluids, where angular momentum currents are driven by a viscous response to gradients in the rotation rate of a single fluid, just a normal fluid. Now we have a two-fluid picture, and the normal fluid keeps its contact viscously with the crust of the neutron star, but the superfluid has a weird hydrodynamics because its angular momentum transport is some more complicated function of the lag between the local superfluid rotation rate and the normal matter rotation rate. Now, this, in the case of neutron stars, brings in a lot of richness because in the case of helium-2 at least, the coupling between normal matter and the vortex lines is just linear drag forces, linear in the velocity difference. So the equations are interesting, but they are linear. But as soon as you bring in stochastic distribution of pinning centers and what can happen there. It of course has a linear limit, but there's a whole rich behavior, including stop and go, in extreme nonlinearity, which is the major glitches, and everything in between. So that opened the new window, and we wrote a paper on this with David Pines and Phil and Jacob Schaum in 1984, and then it got on from there. It still is the major explanation for neutron star dynamics in terms of creep in a pinned superfluid.
Oh, thank you so much, Ali, for bringing in the astrophysics connection to Phil's work. Do you want to sneak in just one short personal anecdote for those who are non-physicists in the audience, particularly Susan, his daughter, who's here?
Well, in 1975, Duncan will remember this, we were both physics graduate students. I came into the lab one morning and saw Duncan sort of straight out of the staircase, I think the corridor, and he says, "Tough shit. Phil has put a little note on the bulletin board in the TCM group, in Theory of Condensed Matter group in Cambridge. This was at Cambridge, announcing that he is changing his appointment and he'll now spending his time in Cambridge instead in Princeton." So we were both sort of very surprised and shocked. But of course, Phil took very good care of us. He had arranged, he arranged from some grant somehow to pay for our transatlantic fares, and found visiting student positions for us in Princeton, took us over with him, and we both finished in Princeton. He found money for us and so on.
Okay, thank you so much. Can I open up the discussion overall? Duncan, do you want to comment, by the way, on this transition from Cambridge to Princeton?
Yeah, I guess, yeah, it was a breath of fresh air, actually, because in Cambridge, it was the rest of the group, mainly band structure people, apart from Sam Edwards, who only showed up on weekends. So it was like we were the small group of interacting people. And of course, Phil didn't attempt to hide what his feelings were about band structure calculations. And so it was us against them. And in some way, in fact, after Phil left, a senior person made a comment, no more renormalization group. We don't want these kind of trendy things going on here. We want honest, honest calculations to fit the bumps in the surface spectrum of argon on nickel surfaces or something like that. But so Cambridge was actually so it was a tremendous transition to go to Princeton. It was actually a very interesting experience, and yeah, Phil got us arranged, and he got me a flight on a U.S. Air Force flight repatriating people on a vacation. So I flew from an air base near Cambridge to an air base near Princeton in McGuire Air Force Base for a $5 fare. Paid on his Air Force contract, which he'd been using.
Is it true that he taught you to drive? There's a
I had to take. I failed my driving test in Britain 3 times before trying to get it before I came, so I had to take it in New Jersey. But he took me to the Morristown Armory to take the test. In his car, he carefully reconnected the seatbelt warning sign because it. But then this very fat policeman got in the car with me, and he was annoyed by the buzzer. He didn't want to put his seatbelt on. And I think the driving test was just to do parallel parking in a space big enough for a Lincoln Continental. This was in the later thing, and do one 3-point turn in an empty road. And the New Jersey driving test, which Phil, well, I guess he gave me the car to go and take it in anyway, and took me there. It was a pinch, right? All
right. Good. Okay, thank you. Are there any comments from the greater audience? Basically.
Hi.
Yeah. Yes, Chuck. Hello.
Hi.
So good
May
to see
I
you.
make a comment?
Of course.
Was 1962 when I met Phil, and John Rowell had been doing, along with Ivor Gieber, had been doing tunneling experiments that showed small wiggles in the IV characteristic. And so Bob Schriefer was at Penn. I had arrived as a postdoc. And Bob and I went up to Bell Labs, which was first time I had met Phil. And we went in his office, and Rowell, John came in, showed us some data. And in Rowell's second derivative data, there were some very sharp peaks that appeared in his IV characteristics. And Phil made the comment, maybe those are Van Hove singularities in the phonon spectrum. Well, I was sitting there not certain what Van Hove singularities were, but when we went back, when I went back to the University of Pennsylvania and went to my office there, I worked out a little theory of how this would appear in the DI-DV characteristic and sent it off to Phil. And then Phil said, Doug, you should present this at an upcoming meeting. There was a, I think 1962 or 63 meeting at Colgate. And it turned out that was my first paper. I thought Phil would join me, but he said, no, you work this out, or just put in this little paper, which was both very generous of him and was very special for me because I had completed my PhD. I had not written any papers. I was long in the tooth because I'd been an experimentalist for 5 years and quite uncertain what would happen. And here Phil had made this suggestion and then told me, no, Doug, you publish it. Later, he and I published a longer paper on it, but he was very generous in that. Later on, as one knows, I think he felt that, as was said, computers were misleading people. And particularly, I think he felt some of the calculations we were doing were, as he put it, misleading people. But he was always very friendly to Diane and myself. And as you know, he played tennis as a young person, but he also played tennis as he grew older. And sometimes Diane and I and our daughter Anne and Phil would play doubles. And I remember particularly one evening, I think we were in Spain, but I'm uncertain where we were. We were abroad. I said something to Phil about, or we said something about going to dinner, and Phil said, oh yes, he would come. It turned out to be one of his birthdays. So Anne and I and Diane sat at this small table and celebrated one of Phil's birthdays. And as I say, he was early in my career, very special to me. Thank you.
Thank you so much for sharing these precious reminiscences. And yet again, another example of Phil being so generous with young researchers. Are there any other?
Dario Tosati.
Yes, Dario.
Yeah, briefly, I became Phil's postdoc by accident in Cambridge, 1972. Basically because his door was always open, but people were too scared to walk in. But I, being an Italian dog, I would not know all these subtle details. So I walked in, I had some data to discuss, and we ended up becoming collaborators and in fact, very, very good friends. I have a record which is, I convinced him to join me on a wrong paper. So I hold the record of having Phil write and sign a wrong paper on some surface physics thing, which was still a very inspiring paper, but I think in that particular case it was wrong. about his driving. Actually, my experience was always opposite to what you guys are talking about. He drove us around Cornwall in his place, and maybe it's my Italian sensitivity to driving, which is different from the average Anglo-Saxon. I always found him very, very reasonable as a driver, and he was very conservative. Once I drove to his place in New Vernon with an old American car, and you said, "Ah, Ario, you got a guzzler." He was very preserving nature and things. And I must now more officially sort of thank him for all the good things that he did, not only for me, not only for physics, not only for the community, for the developing country work that we do in ICTP Trieste. He was always very supportive. I remember because some bureaucrats wanted to have some rather strange director in ICTP, and he was on the committee and he fought very hard. And when Miguel Angel Virasoro became the head, he sent me a message saying, "Hey, we won, we won." And Miguel Virasoro has been a great director for 7 years, thanks to Phil Anderson. And of course, Bhaskaran, who is in the audience, is a witness of all this. He met Phil at our place, and then this did a great big things. The other thing, I think Phil really would go down in history, not only for his science, but has been said as a philosopher. I think more is different is a great thing, but also many other points of view, in particular, his lack of respect for many things, for authority and for prejudices, including religion, which seems to be, a very rare. Once he said now that sex anomalies are no longer a taboo, we atheists are the only sort of category that sort of is not worth talking about in public. And I'm very responsive to that. I think that's a very nice and sincere message to let people free to be original and contrarian when it's necessary, even in that viewpoint. Okay, and thank you very much, Andy. This was a marvelous, and Premi, it was a marvelous, really marvelous occasion.
Thank you so much, Ario. I think, unfortunately, we only have
Premi, Greg Bobbinger has a question.
Okay, we have time for one more question. Greg?
Well, it's actually an anecdote about how I first met Phil Anderson. I first met him when his back was turned, in fact. I was a graduate student at MIT with Horst Stormer, and Horst had invited me to come down and present some of our high field data on activation energies in fractional quantum Hall effect. And I was sitting in the back of the room as a respectful student, and Horst Stormer's idea of a practice run through of my talk was to come to the session early, sit down next to me, and leaf through my already completed view graphs. And after doing that, he then pointed to the back of Phil Anderson, and he says, "That's Phil Anderson, that's Phil Platzman, that's Chandra Varma. Now go give a great talk." And so in the middle of my talk, one of our ideas was that we had evidence of these localization tails at low temperatures, that maybe it was the fractionally charged quasi-particles that were undergoing variable range hopping, and maybe it would be a way to measure the fractional charge. Well, I plotted the fit parameters, which were supposed to be a straight line in magnetic field. This is in the day of view graphs. So I had a plot that had just a scatter of data everywhere, and then I had a straight line going through it. And before I could say a word, Phil Anderson leapt to his feet and said, "How do you know all of that data lies in the same plane?" And that was my first interaction with Phil Anderson. It was not the most enjoyable interaction. We had many, many more through the decades, but I'll never forget that story.
Thank you so much, Greg. Thank you, everyone. I think it's time to round out our roundtable. We're, of course, awash with reminiscences, and we will continue to enjoy our precious memories and Phil. So let's give a hand to everybody. And
I'd just like to thank Piers and Premi for organizing and running this. It was really a pleasure.
Thank you.
You're welcome. Okay, good. Okay, everyone, thank you for coming to this session on Phil Anderson. There in the ICAM Global Summit, there will now be a 10-minute break, and we will reconvene in just under 10 minutes for a talk by Professor Michael Cates. Thank you indeed.
Thank you very much, Piers. Thank you.
Thank you, Piers. Thanks, everybody.
Thank you. Thank you, Piers.
Piers, do you have the agenda for the next 2 days?
Yes, it's all up on the ICAM website. If you Google ICAM Summit 2020, you'll see it all there.
Thank you much.
I made a copy, so I'll send it to you, Greg.
Yep. Okay. Thank you very much.
Thank you.
Thank you, Piers.
Thank you.
Okay.
Thank you. Thank you. Goodbye. Good night. Good morning.
Thank you.
Yes. Thank you. So good. Good
Thank
night.
you, Susan, for coming.
Hi, Susan.
Yeah.
Hi, Aria.
Bye, everyone. Thank you. Thanks for organizing the meeting.
Bye, Ario. Bye, friends.
Okay. Good night, Gambati.
Good night. Good night. Thanks.
Okay. Okay, Mike, I see you're there. We're going to be rejoining together in about five minutes or so.
Yeah.
If you
So
want to check your
yeah, just 1 second.
Yeah.
So screen share is the method, is it?
Screen share, yes, indeed, yes.
Yeah. I have some movies which I can do without, but I would probably a good idea to see in advance whether they're going to work.
I think you should check that they work.
Yeah. Yeah. Okay. Okay. Just 1 second. Okay. So, of course, I have 2 screens, so I'm not even quite sure what happens when I share one of them.
Experiment when you try this.
Yeah.
I think it's usually good to put your view graphs, your PowerPoint in the second screen, and then share the entire second screen, and then play within that second screen, if I remember the right way of doing it.
Yes. Just 1 second. So, yeah. So I'd need to actually reconfigure my PowerPoint so that it's not mirroring. The 2 screens aren't identical, which I can do. Let's see. Yeah, okay. That didn't work either. So let me try and sort this bit of it out first.
There's plenty of time.
Yeah. I mean, it's possible we'll just end up with the, the slide sorter still visible, which is fine. So let's see about sharing the screen with the slides sorter still in front of me. So have you? Okay, I can.
It should be open to screen share. So
yes, it is. Whiteboard or okay. Let me just press advanced here. No, okay. I'll go back to basic and screen share that.
Okay, good. We're seeing.
Well, what are you seeing? Because are you?
We're seeing a PowerPoint, but you probably can't see it.
That is the problem.
Yeah, so that's why you've got to put your PowerPoint in your second screen, and when you go to screen sharing, share that screen, not that program.
Right. Stop share. I'll share screen again.
But don't go to the program, go to the actual screen, the full screen.
Well, it's giving me, on screen sharing, it's giving me a choice between a whiteboard and PowerPoint rather than a choice between one screen or another, which I find slightly disappointing.
Oh, I don't know why that is.
Hmm.
Huh. I wonder if that's the settings on this Zoom account.
Mike, try to share that PowerPoint and then play presentation. Let's see what happens when you press play presentation.
Okay, so I'll share that.
Okay, now play presentation. Let's see what, because your first slide is
okay.
Yeah, press this play button, whatever it is, and your first slide is blank. So go to next slide, advance to next slide.
Yes, the trouble is though that I can't see my, unless I use the thing along the bottom.
Oh. Oh.
Yeah, so this is not.
Can you advance with? Okay, now we see something. We see the movie. We see the movie.
Yeah. Okay. Well, that's good. Now the problem is though that I'm likely to lose it in the same sort of way because I just need to move the cursor to the wrong place and it just goes off to the side like that. So I'd like to kind of stabilize it in this condition if I can. And I think what that means, I think it's to do with. Mm-hmm.
If you use cursor to advance slides, I mean, you know, keyboard cursor on keyboard, like page or whatever. Oh yeah, okay. So okay. So the keyboard can advance your slides. And
yes.
Movies.
So then I should probably just not touch my actual laptop at all, except via the arrow keys over here.
Yes.
Okay.
Yes. So basically, use arrow keys to advance slides.
Yeah.
But to start a movie,
most of them start automatically.
Okay, if they start automatically, that's fine.
And if they don't, I will probably just
because otherwise, usually to start a movie, you need to use mouse and click on movie. You know, otherwise, But try to use keyboard most of the time and. Yeah, avoid mouse unless you really need to start a movie.
Yeah, that sounds good. Okay, so I think let's just let me just go on through this a bit. Yeah, so that one's starting by its own accord. That one did as well. So I'm interested in the bandwidth of these. I mean, are these actually showing as movies, or are they?
Yes, they actually look fine. They actually look fine.
Really
Keep in mind that the frame rate on Zoom is lower than usual.
Yeah.
So you know the screen updates happen not as frequently, but nevertheless, for the purpose of this illustration, it's okay.
Yeah.
We do see movie. We do see things moving. All right.
Good. So,
and they don't freeze. Most importantly, they don't freeze.
No, exactly. Okay. Well, so that's very encouraging, and I'm hoping to do it like this then. So the worst case scenario, as I do have a non-movie version as PDF, and if everything crashes out halfway through, I can just switch to that. But I will try to use these. Okay.
Good. We're in good shape. We'll just wait for a few more people to arrive, and hopefully Christina, who is going to do the introduction. But you never know with these summits whether everyone's got the times right and everything else.
Yes, exactly.
Hello, Mike, across the waves. How are you?
Hello, I'm very well. That was a really good session just now.
Oh, thank you.
Andrew's talk was fantastic.
Yes.
That was just absolutely hit the button. It was great.
Yeah. Oh, I'm glad. Hi, Victor.
Hi. I really enjoyed. I mean, great. Absolutely great session. Yes, and the book. I mean, I didn't know the book is coming, but that's a fabulous session. And I also look for the session tomorrow. This science at the age of H index.
Yeah, that should be very interesting.
Yes, I'm looking also toward that one session as well.
Well, it was particularly interesting given Doug Scalpino saying that he had graduated from Stanford without writing a paper, and that his first paper was after meeting Phil. It shows how times have changed.
Mm-hmm.
So just so I know, by the way, on your screen, it's just my slides, is it? Or yeah, okay. Or I think if you want to, you can put those in a separate window and still see people's faces, but that's up to you and not up to me, I think.
Yes, or we can just see your, I usually just have whoever's talking.
Yeah, that's okay. But so in principle, people might be looking at me, so I should
yes, absolutely.
Avoid physically embarrassing gestures and things.
Yes, because
I'm looking at you now.
I've just I got a bit more light.
Yeah,
I think that's probably all right.
Yeah. So the standard procedure is, for sharing, that it shows your share screen, and usually, typically, it shows a small swivel window at the bottom of your face. Of course, you can turn it off, or you can turn to gallery view and see everybody's faces, if you make extra effort. But by default, it shows your small face in the corner. So just, beware of that.
Yeah.
And also, Pierce, is this all recorded? Right?
This will all be recorded.
And posted, will be posted, right? Yeah.
Yes, it will be posted. It's all running live and we're going to record it. I'm just hoping that Christina will join us. If not, I will present the talk. We'll give it just 2 more minutes.
Yes, and this recording, I suppose it's set up so that records, share a screen and the active speaker, right?
Yes, it just does that automatically. There's nothing we can do to avoid that.
Actually, on what I found on the Zoom setting, what I found in my recorded. Okay. So what I found in Zoom settings for my class, that actually default setting was record shared screen and gallery view. That means everybody's faces.
Yes.
And that was not for my class. So I changed it manually. That was default. So I had to change it, in the settings to record shared screen and active speaker. So then it records only one person at a time, rather than everybody in the audience. That's generally better.
Okay.
But that's in Zoom settings on the website. You have to go to the website. I set it there.
Well, I think since it looks like we've somehow lost Christina, we're going to go ahead. So let me just, Christina, are you there? No. Okay, so let me introduce Mike Cates. I know Mike Cates for many years, since he was a junior research fellow at Trinity College, Cambridge. He was for many years professor of natural philosophy at the University of Edinburgh. And since 2015, he stepped into the illustrious position of Caucasian Professor of Mathematics at the University of Cambridge. Mike is known for his work in soft condensed matter physics, and we're really excited to hear about his current work today. He's worked in areas such as colloids, polymers, liquid crystals, and granular materials. And he has, in some sense, in the spirit of Phil Anderson, developed interesting mathematical models to capture the essence of these emergent systems. And so we're really excited about his talk today. Thank you, and welcome, Mike, for coming to join us today.
Thank you very much. I hope people can hear me. Normally, I would welcome questions by way of interruption, particularly as I'm aware that this topic is not necessarily familiar territory to many in the audience. I don't know if it'd be possible, if people have urgent questions, to put them in chat for peers to relay them to me. But if not, unfortunately, you'll just have to wait to the end. First, I just want to say how much I enjoyed the session just now on Phil Anderson. I only met him a small number of times. There's one anecdote which I maybe even, I wasn't there for the whole thing, so maybe even someone said this, but on one of his visits to Cambridge after he'd returned to Princeton, I think it was, this is the story I was told anyway, that Sam Edwards and Brian Josephson and Phil Anderson went to the Three Horseshoes pub in Madingley for lunch. So that combination, 2 Nobel Prize winners and the Cavendish Professor of Physics, and they weren't allowed in because they weren't wearing ties. So that's a remarkably British story. Anyway, I think they had lunch in the bar, but not in the restaurant. So anyway, I'm talking today about active matter, particularly the issue of active phase separation. I'll say what that is in a minute. I want to acknowledge my collaborators here, particularly for this talk, Fernando Caballero, Elson Chung, and Cesare Nardini, and various sources of funding at the bottom. No, come on. Having just learned to do this, I now, of course, fail to advance the slides. Let's just see. Oh, that worked. Okay, so now the agenda is here. I'll say a bit about active colloidal particles, and both living and dead. And I want to emphasize in this talk the way we construct field theory type descriptions. So these are quite familiar classical scalar field theories. And if you know what model B is, that's the type of theory I'm talking about. I will explain that later, in the absence of time reversal symmetry. And for this audience, I want to explain that lack of time reversal symmetry is not about magnetism in these systems. It's about systems which are continuously dissipating heat. It's the second law. You have a system which is constantly using up energy. For instance, swimming microorganisms or bacteria which are whizzing around, they have an energy supply and they're using it up. So it's actually CPT, symmetry breaking, if you want to be formal about it. So I'll describe some of these scalar continuum theories that we use for this, talk a little bit about phase coexistence. There's a particular angle there which is to do with the behavior of droplets under conditions of phase equilibrium, where you can, in active systems, get this strange phenomenon, which I will talk a bit about, which is reverse Ostwald ripening. That leads to microphase separation. And towards the end of the talk, I want to talk about the quantification of entropy production, because that's this issue of time reversal being broken in a field theory, and asking the question, how do you quantify the extent to which that symmetry is broken? And we do that through the entropy production, which is a computable thing in the field theories I'll be talking about. So these are the types of system. You could imagine a liquid, tank of liquid with, say, a bunch of swimming bacteria, which are moving around. They have self-propulsion, motile organisms. So that's something which at a large scale may look a bit like Brownian motion, but it isn't. It's not thermal, it's dissipative. In the last decade or so, people, colloidal experimentalists, have found ways to make very clean systems that behave in a broadly similar way. These are these autophoretic colloids. So what you have here, this drawing is a colloidal particle, say 1 micron roughly. It has an asymmetric surface. For instance, the front of it could be coated with platinum, at the back with gold, something like that. You put that in a bath of chemical fuel, like hydrogen peroxide, and it starts to self-propel. So these particles start swimming under their own speed. And there are ways of controlling whether they swim or not with light. There are others where light is the fuel. So there's this whole industry in the experimental colloid realm of self-propelled colloidal particles. So here are some of these particles. This is from Paul Chaikin's group in NYU. These are controlled by light. So you see that while they're self-propelled, they undergo this clustering. They're making these little crystallites. In my talk, I will be talking mainly about phase separation between a dilute phase, so these individual particles here, which we call a vapor, and a liquid. I won't talk about crystallization. But here you see if the light is turned off, these become ordinary Brownian particles. So this is now thermal motion. This obeys time reversal symmetry and detailed balance. If you turn the light back on, you switch back to this state with the phase separation. So this clustering or phase separation is caused by self-propulsion, and this goes under the name of motility-induced phase separation. Motility being the biologist's word for the ability to move autonomously by using a fuel of some kind. So if we look at this at the microscopic level, and my talk will mostly about field theory, so this is just background. The simplest way of thinking about this is something called the active Brownian particle. So what we have here is a particle which has a fixed speed, but this speed it is in a particular direction, which is in a fixed body axis. So think of that autophoretic colloid, which has a front and a back, so it knows which way it's self-propelling, but that axis is itself diffusing, so it has angular diffusion. So if you imagine the path that that particle will trace out, it's a persistent Brownian motion. It looks like a semi-flexible random walk. Speed v has a rotational diffusivity dr, orientation unit vector u. And if you coarse grain that, or an n non-interacting active Brownian particles, you get a random walk or a set of random walks with a certain diffusion constant, which involves this ratio written here, the swim speed squared times the angular persistence time tau divided by the dimension of space. So if you coarse grain that, it looks like Brownian motion. And if that was all that there was, that coarse graining would actually restore time reversal symmetry, because Brownian motion has got time reversal symmetry in the sense that I mean here. But in fact, as soon as you confront these particles with any kind of challenge, like interactions, the time reversal symmetry is visibly gone. So here's a movie, which I hope you can see, of a asymmetric cog in a bath of bacteria. And you'll see that this cog is rotating continuously in the same direction. And this is to do with the persistent motion of these motile particles. Essentially, you have a rectification which turns into a macroscopic motion of this object. And the violation of time reversal symmetry in this movie is, I hope, self-explanatory. If I ran that backwards, it would be running in the opposite direction. So that's the interaction of particles with an obstacle, or a rotatable obstacle. This is a set of active Brownian particles which are interacting with each other by purely repulsive interactions. So in a thermal system, if you have Brownian particles with purely repulsive interactions, then of course you get a uniform fluid. You don't get a phase separation like this one between a vapor and a liquid phase. And I'll have more to say about this type of movie later on. But this, as I mentioned, is this phenomenon of motility-induced phase separation. So before moving on to the field theory, just a bit of kind of mechanistics about where this comes from. What you find with self-propelled particles, which is also true of human beings when they're walking down a high street and looking in the shop window, if there's something interesting in a shop window, you'll find that there's a higher density of people at that point in the street than elsewhere. So in the absence of detailed balance or thermal reversibility, there's a general tendency of particles to accumulate wherever they move more slowly. And thermal Brownian motion is the exception, because you know that in a thermal system, if you have a region of different diffusion constant, but the same temperature and the same potential, you do not get a buildup of particles, because that would not be the Boltzmann distribution. The Boltzmann distribution says exponential minus V over KT. If V is constant, KT is constant, but the mobility is variable, you do not get accumulation. But in the more general case of motile particles, you do. And also such particles in many cases, like when they have collisions, so hardcore interactions, as I've just described, tend to move slowly where they accumulate, so where they're dense, so that you have a positive feedback loop. And that's the basic physics behind this type of phase separation, and is completely understood in simulation terms for these active Brownian particle ABP systems. If you look at experiments, the situation is more complicated because there are other interactions. I described these autophoretic colloids, and there you don't have a hardcore repulsion between the particles. Each particle actually self-propels by setting up a gradient of reagents and products from the chemical reaction around it, and then other particles see that gradient and can be entrained by it. So there are what we need is a more general description, and something this more general description should hopefully explain is this phenomenon called cluster phases, which is where instead of going to a complete separation, so like a liquid vapor or a solid vapor phase separation, you get partial separation into clumps of finite size. And here are some pictures. There are more spectacular pictures than this in the more recent literature, but these were the early ones. So if you look at the middle picture here, you see these finite clusters. If you watch the particles in those clusters, they leave and rejoin. So they're living in that sense. And it looks like a mini phase separation, and you saw it also in the movie I showed earlier on with bigger clumps, that in many systems, these clumps cease to grow at a certain scale. So that's the cluster phases, and that's one of the targets for the kinds of theory that I'm going to talk about next. So what I want to do now is tell you or remind you about the way in a classical system, so a system of diffusing particles, h bar equals 0. So think just of an ordinary room temperature liquid vapor transition, or probably actually better, a binary fluid transition, so a mixture of alcohol and water that's going to phase separate. What is the way to talk about that theory in the most general condensed matter physics sense? So what we need is a scalar field which describes a composition variable or a density. So this is phi, and it's conserved because we have a fixed total number of particles. So its time rate of change, as you see in the top line here, is the negative divergence of a current. And in, for instance, colloidal particles, which might have attractive interactions, the current, to a first approximation, is some mobility times the negative gradient of a chemical potential, mu, plus a noise. So this is where the thermal noise comes in. So this, what I'm writing down here, is a Langevin equation for phi. It's a thermally fluctuating scalar field whose basic motion is this conserved diffusion. And written down there for the chemical potential is the one deriving from a square gradient theory, which I shall now expose. So in these equations, first, lambda is a unit white noise. So that's Gaussian delta function correlated noise. There's a mobility in front of the grad mu term, which I've set to 1. And the diffusion constant D in a thermal system is related to that by kT. And that mu is the chemical potential you get from a square gradient theory, so a phi-4 theory, the thing that you do, that you look at in the Ising model if you want to do the renormalization group, for instance. So that chemical potential is the gradient of a free energy functional, which involves a local piece, which is just this quadratic potential on the right with 2 minima when A is negative. So that's the case when you get phase separation. And it has a square gradient term. So we know about the steady states of this system. You can construct them just knowing the local part of the free energy by basically doing a global minimization of the free energy. And the result of that is the common tangent construction. So the system in the region, if you try to plant the system in the region where you're in this bump of f of phi, it will phase separate into, in this case, coexisting volumes with the two phase densities there, given by those 2 minima. And more generally, the equilibrium conditions are that the chemical potentials in these two coexisting phases are the same. So mu1 equals mu2. So that's df by d phi, because in the bulk phases that coexist, there are no gradients. And the other condition, so that says that the green line has to touch the red curve with the same slope at these 2 points. And the second thermodynamic condition is equality of the pressures, which says that the 2 intercepts are also the same. So this is the thermodynamic construction, which is kind of undergraduate physics for phase coexistence in a scalar field. So that's all fine in a system with a thermal equilibrium, a Boltzmann distribution, detailed balance, and in the context of these equations, time reversal symmetry in the dynamics. And by the way, if you're wondering where time reversal symmetry comes from, it comes from the fluctuation dissipation theorem, which is connecting the noise to the mobility. So it's not that there's no damping in the system, it's that the temperature exactly compensates the damping to give you the Boltzmann distribution. So the first thing I want to tell you about, which is several years old now, is what is the minimal way of extending this dynamical description. So that was called Model B. What's the minimal way of extending that to a system which is got these active particles instead of Brownian particles? And the simplest way is actually written down here. We call this active Model B. And it has an additional term. I put a hat on the chemical potential mu to say that this is no longer no longer has a free energy structure. So I can break time reversal symmetry by breaking the free energy structure. And it may not be altogether obvious why it's true that if you don't have a free energy, you don't have detailed balance and you don't have time reversal symmetry, but actually I will, if I have time, prove that later on when I calculate the entropy production for this theory. So anyway, that lambda term isn't anybody's functional derivative. So that's a way of constructing a theory which doesn't have a free energy, doesn't have a Boltzmann distribution, and this is the minimal extension of model B to describe the case of active phase separation where I don't have time reversal symmetry. So let's see what that does. Well, interestingly, the first thing that it does is it changes the rules for coexisting phases. So unsurprisingly, in the middle part of this free energy curve, where the scalar field phi is around 0. So phi is a density, but it's not literally a density of particles. It's you put a linear transform on it so that it's essentially -1 in the vapor and +1 in the liquid. This is the way you tend to do these things. So what you find that lambda term, even though it's only a gradient term, and so at first sight, if you start thinking about the bulk phases, you say, oh, well, the chemical potential's the same because there's no gradient contribution in the bulk phases, and there's likewise the pressure. So I could equate the chemical potentials and the pressures, and that would be unambiguous, given that the only term I've changed is a term in the gradients, but it would no longer give the correct answer for the phase coexistence. So to actually calculate the phase coexistence, what you do is you have to assume a phi that depends on x, so a one-dimensional interface. So imagine I have a flat interface between my two bulk phases. I require 0 current, so that actually itself, it does say that this chemical potential, like quantity mu hat, has to be constant in space so that the chemical potentials are equal in the bulk phases. But when you solve for a 0 current solution with 0 gradients at plus or minus infinity, you do not get the thermodynamic construction. You get a so-called uncommon tangent construction, where the offset in what would have been the pressures of the two phases is proportional to this lambda term. So it's proportional to the coefficient of this term that breaks time reversal symmetry. So I may come back to this a bit later, but actually what this actually means is that even within this scalar field theory, that funny new term, that lambda grad phi squared term in living in the chemical potential equation, is effectively creating a pump that pushes stuff from one phase to the other phase, because this grad phi squared at mean field level is only non-zero near the interface. So near the interface, there's something about this term which is essentially pumping matter from one phase to the other. And so I'll come back to this a little bit later on. So this a failure of the common tangent construction, so we call that anomalous phase coexistence, is definitely a thing for active particles. You can confirm it for this theory. You can confirm it algebraically on models where I have particles that are swimming around with a speed that depends on the density. That's one of the ways of understanding the motility-induced phase separation that I told you about before. If you actually do the same thing for active Brownian particles with hard core collisions, you again have anomalous phase coexistence, but it's not quite this analysis route. What you find in that case, for technical reasons I don't want to go into, is that the chemical potentials are different, but the pressures are the same. So there are subtleties here, but in terms of the types of scalar field theory I'm talking about with active model B, it's quite clear what's happening and the unusual role of this new term that breaks time reversal in the dynamics. So that's the equations again. So the blue part is the equilibrium part, the red part is new. It gives us at least one good thing, which is this shifted phase boundaries. It does not give us cluster phases, a number of other things it doesn't give us. If you look at this equation, the current is the gradient of something. So this will never give you spatially circulating currents in steady state, which is another thing that you can arrange in active systems. It's quite easy to arrange that, in fact. So there's definitely something missing from this equation. And it took us a year or two scratching our heads, and here it is. So what is written down here then, so this is called active model B+, has all the terms that definitely break detailed balance or time reversal. So there's two independent terms that do that. One is the lambda term in the chemical potential, which I've already described. The other term is this zeta term, which sits directly in the current. It's not the gradient of anything, so that means the current can now have a curl. And also, the reason we didn't spot it in our first papers on this is that this bunch of funny gradients, which are the only other thing that you can construct with two grads, well, by the time you reach J, it's got 3 gradients and 2 fields. That combination that I've written down there vanishes in 1 dimension. And so this term only exists in more than 1 dimension.
Mike, can I ask a question?
Yes, please.
Yeah. So are you writing down J on a kind of symmetry constraint basis, or is it something that you can derive from some action or other approach to things?
Well, so this is like a Landau-Ginzburg expansion, and what I'm doing at the moment is basically just doing a Taylor series in gradients and fields.
So I see. So I could have an action there which I put in some imaginary vector potential and differentiate it to get your J that you've got here.
You'll see something very like that in a minute.
Okay, thank you.
So yeah, so think of this just as in a kind of a Landau-Ginzburg expansion, full frontal direct, and you ask what terms can you get at each order in gradients and fields, and at the same order of lambda is also this other term. Of course, I could go to higher order and life would get progressively more complicated. But as in Landau-Ginzburg theory, one would tend to see what you get at each stage and stop when you're satisfied with the results.
And why do you group those 2 terms together multiplied by zeta? Where does the one come from?
Well, that combination, I've chosen to write that in such a way that that whole thing, that square bracket, vanishes in 1D.
Okay, thank you.
If I just write out independent coefficients of those 3 terms there, only 2 of them are linearly independent, because the gradient of mu is a bit like one of those 2 terms. So at that order, there are 3 independent terms. There are 3 terms of which 2 are independent.
Okay, thank you.
Yeah. Okay. So a corollary of that is if I think of these calculations of phase coexistence between dense and dilute phases, is that this new term, this zeta term, actually has no effect at all for a flat interface. So it has no effect on bulk coexistence, but we will see that it has interesting effects when I have curved interfaces, and that's because in more than 1 dimension, this object here that multiplies zeta actually, well, as I say, it vanishes in 1 dimension, which means also that it vanishes when phi is a function of 1 variable only, so that actually this object is it comes away from 0 only as I curve the interface. And curved interfaces play quite a big role in the kinetics of phase separation, so that's something that will have effects. Okay, so but no effect on bulk coexistence, at least not at the level of any kind of mean field theory. Okay, so why am I showing you this now? This is something that happens in active Brownian particles. This is a simulation of active Brownian particles. The yellow regions are dense, the purple regions are the vapor. And this hasn't gone all the way to full phase coexistence, but one thing you hopefully could have seen in that movie, as it reaches a fairly late stage of phase separation, is that you get these voids, and you can see them in this picture now, these purple voids inside the dense liquid phase, which is yellow. And these voids have a certain life cycle. They are generated in the middle, and they pop out at the boundaries. So that life cycle of these little bubbles, once I reach a steady state, which I'll show you in a minute, has a manifest visual breakdown of time reversal symmetry. And it turns out that to see this, you do need this zeta term. So let's see what the next slide is. Yeah, so this is a simulation of active model B+, and this is a steady state now. So I have this big blob of fluid which happens to cross the periodic boundary conditions. Part of the phase equilibrium I'm seeing is these voids, these bubbles inside the fluid, and you could see there this life cycle where they're formed in the middle of this blob of fluid, and they progress to the outside. So later, if I get the chance, I will run that movie backwards, but it should already be clear to you that that visual observation of the steady state is showing that this theory is violently not got time reversal symmetry in its kinetics. And the same is true in principle of active model B without the zeta term, but it doesn't have these bubbles and it is much harder to see. So this is the model again. Here is, so that thing, I'm now going to call that J zeta. And let's see if we can get a little bit further with our understanding of this model. And the first comment here is that because of the conservation law, although this J zeta can have a curl, that's invisible as far as phi dot is concerned, because I take the div of J, phi dot. So there may be a curl in the current, but if I'm only interested in movies that show me a time-dependent set of configurations, so a time-dependent series of phis, of density profiles, the curl of J is invisible. So if I cross that out, then the remaining part of that current is the gradient of something. That's just Helmholtz decomposition. But familiarly from electromagnetism, the thing that it's a gradient of is something like a Coulomb integral. So I need to look at the divergence of this current. And in 3 dimensions, the results are written down here. I need to do a 1/r integral against div J. And then the gradient of that mu is the same as up to a curl as the J that I started from. And this is useful because we're used in thinking about phase equilibrium, we're used to thinking about chemical potentials. We try to avoid thinking about currents. So given the form that I said for this funny J term, which is this combination of gradients that vanishes for any flat interfacial profile, what you find then is that this looks like this chemical potential, which is a scalar, looks like the Coulomb potential from a dipole density. And the dipole density, these dipoles, if you think of it as an electrostatic problem, they live on the interface between phases, and the density of them depends on the curvature of the interface. So I get a non-local contribution to this chemical potential-like quantity, which depends on interfacial curvature. So this will have significant effects on behavior. So as I've said then, this zeta term changes the way that the chemical potential relates to the curvature of an interface, if there is curvature of the interface, and that has dramatic consequences for phase separation under conditions where the separation includes droplets of one phase in another, which is typically en route to phase separation. That's certainly what you have. Okay, so I'm sparing you the gory details. If you do a mean field phase diagram for this active model, so I'm looking at what the steady states are like, when do I have phase separation? I told you that the active terms shift the phase boundaries. And what's plotted here is the mean field phase diagram, so that doesn't care about zeta. And in terms of my other parameter, lambda, if the phase boundaries shift with lambda, left to right, that's shown by moving up the vertical axis here. The spinodals, which is the point where the curvature of the local part of the free energy changes sign, so that's the point of local instability in the kind of phase separation model B I'm talking about, is unaffected by activity. So as long as I have flat interfaces, this is my phase diagram. So the kind of mean field phase diagram, which assumes coexisting phases with bulk phases and flat interfaces, doesn't care about zeta, and this is what I should see. And if zeta is absent, in other words, for the active model B with only the first term, only the lambda term, this is actually what I do see. So there are plenty of simulations numerically on this model with finite noise, but as long as the noise is not too much, I see this phase diagram as long as zeta equals 0. So I see the mean field predictions. But when I do add that second term, which messes about with the currents and messes about with giving me these non-local chemical potentials, I see something else, which is in this region of the phase diagram here. If I turn zeta up to a positive value, what I get is a steady state that has finite bubbles in it. So I see, in that region, I see a uniform liquid with little vapor droplets in it, and these vapor droplets fail to coarsen and fail to establish a bulk phase of vapor. So this is a kind of arrested phase separation. Here's a movie of it. So that we call the bubble phase, unsurprisingly. And you actually saw that when I showed the previous movie, which had this big droplet of liquid with bubbles inside it. It was actually a big droplet of this phase in excess vapor. That's what you were seeing there. So this is an interesting steady state, and I'll say a little bit more about what's happening to those bubbles in there. But if I move on, so there's just a snapshot of the bubble phase. So I'm now going to point out a symmetry of the model, which is this. So if I go back to my equations of motion and I change the sign of both of the active parameters and the field phi. So if I change the sign of phi, what that means is I re-identify the liquid phase as the vapor and vice versa. I'm just changing plus phi to minus phi. So if I change both activities and phi, actually the equation of motion are exactly the same. So this active model B plus, if I just choose different signs for the zeta and lambda parameter, magically I've just switched the scale on there. So now the black regions are the dense regions and the vapor is the orange color. So this is now cluster phase. So active model B for one set of parameters can give you a vapor phase with bubbles in it, so a bubble phase, and for differently chosen parameters can give me something like the cluster phases that I was telling you earlier were reported experimentally. Okay, so there's a phase diagram. So the sequence of states along the bottom is the one with the high value of this zeta parameter. If I turn zeta off or just down enough, I see a regular phase coexistence with just the bulk coexistences, which is the top four figures left to right. So the new phases are the middle two at the bottom. So how do we understand that? Let me say a few words about how we understand that. So where do these new phases come from? Well, so now I need to tell you, or hopefully in some cases remind you about Ostwald ripening, which is a phenomenon that happens in alloys, metallic alloys, as well as in binary liquids and vapors. So at a curved interface, essentially reflecting the physics of Laplace pressure, there's an uplift in the chemical potential. So in the neighborhood of the interface, the chemical potential at the surface of a droplet, and I'll talk about droplets rather than bubbles now, that's the conventional language. Near the surface of, say, a liquid droplet in vapor, the chemical potential is raised by a factor that is proportional to the surface tension, has a d-1 in it, so that it knows about dimensions, and 1 over r, so it knows about curvature. And phi b is the binodal density. That doesn't matter here, that's order 1. So you can calculate the current flowing onto or off of a droplet. So this is the bottom right picture. So what you find then is that if you have a single droplet, it's capable of coexistence with a vapor, as long as the chemical potential of the vapor is raised above the equilibrium value that you'd have for bulk coexistence with a flat interface. So the more important aspect of this, though, is if you have many droplets, because then the ambient chemical potential, so the conditions far away from a given droplet, are set by the mean size of droplets, not by anything else. So what that then means is if you calculate the fluxes onto individual droplets, you can find their rate of growth. It's given by this famous equation at the bottom. And the key thing then, if I just plot this function r dot against r, and this is the unpleasant capitalism of phase separation kinetics, is that the large droplets always grow at the cost of the small ones. So this is very unfair. But what that means is that if you start with the kind of picture at the bottom right, you always end up with one macroscopic droplet, which is then effectively, if it's big enough, a flat interface and bulk phase coexistence. So this process of having chemical potential excess caused by curvature, which drives currents from small droplets to large, that's the physics of Ostwald ripening. And that's how a system that's undergoing model B type phase separation gets to its endpoint of complete phase separation. So I said that this funny active contribution to the chemical potential, this non-local bit, actually gives me a step in chemical potential across the interface. So here it is. I don't want to go into the details there. But the key thing is that gives me a discontinuity in the chemical potential. And what matters is the chemical potential just outside the droplet, because that's telling you the current that is flowing onto or off of it. So that acquires a piece which is written down here, which is also like 1 over R. So it looks like the interfacial tension piece, but it's proportional to zeta. And so if I have a big enough active zeta, so I just have this parameter, which is just in the model as a parameter, and I take it large enough in one direction or the other, I can change the sign of the effective of the apparent interfacial tension in this expression for mu I at the top. So it looks like an Ostwald problem, but under conditions of large activity, I can reverse the apparent interfacial tension. Notice the word apparent. I don't get large fluctuations in the interfaces. It's just to do with these spherical droplets and the current that flow between them. So it's not like having a negative tension in any mechanical sense, but it is for controlling the phase separation kinetics. Okay, so that's the way this term kicks in. And so that's my normal Ostwald ripening. If I change the sign of effectively the interfacial tension, I get this. So now I have a stable fixed point sitting there, which says that if I start with some arbitrary distribution of droplet sizes, they converge to the mean. They all converge. Stuff flows from big to small until they're all the same size. So that's how you can understand the existence of these droplet or bubble phases in the active version of Model B. So if I didn't have any noise, what I've just said would be exactly right. Any initial distribution would just converge to a droplet size. Interestingly, that droplet size is set by the initial number of droplets and the initial total volume of droplets. So it's interesting then that although in the forward, the conventional Ostwald process, the initial condition is forgotten, in the end, I always go to converge on complete phase separation. If I don't have noise in this active Model B plus, I have a permanent dependence on my initial conditions because the droplets just share themselves out uniformly and then stop. But of course, if there is noise, that's not all that's happening. If there's noise, this is back to the movie I showed you before. So if you look at these movies closely, what you see is that these droplets come into coexistence. They sometimes just evaporate, but they often coalesce, and they don't often split. So again, if you look closely at this dynamics here, you would not see the same thing if I ran that movie backwards. There's a life cycle in there. So crudely, droplets form by nucleation of a new droplet, but they generally destroyed by coalescence. By destroyed, I mean they reduce in number. So I tend to go from nucleated droplets to big droplets by coalescence, but then the reverse Ostwald process pulls those big droplets back down towards the mean size. And then that three-way balance fixes the mean size, which ends up, numerically, you find that the steady state mean size does not depend on the initial condition, but does depend on the noise level in the Langevin equation. So it depends on the temperature, if you want to think of that as a temperature. Okay. So if I didn't want to show that slide, so I won't. So if I have a few more minutes, is that all right, Piers? Okay, I'm assuming it's all right. I want to say a little bit now about time reversal symmetry breaking as a thing and entropy production. So we're not talking about magnetism, we're talking about the difference between systems which have time reversal symmetry, which is true for a thermal system, including Brownian colloidal suspension, for instance, in steady equilibrium state. So that's the characteristic of thermal equilibrium. So in a state en route to thermal equilibrium, for instance, by the Model B process, the arrow of time is set by ds by dt positive, and once you reach it, ds by dt is 0. So that, and the principle of detailed balance, which is basically the same statement, says that if I get a thermal system, I wait for it to reach equilibrium, I suddenly turn the movie around and run it backwards. within that equilibrium domain, I cannot see the difference between the forward and the backward moving. So you have an arrow of time or arrow of overwhelming probability taking you to an thermal equilibrium state where time reversal symmetry is restored, even if when you started, because of the second law, en route, it was broken by the entropy production. So the difference, of course, in active systems is that there's entropy production in the steady state. So there's no reason for the time reversal symmetry to ever be restored. But it might still be, particularly if you coarse grain the system enough. So here's the active model B plus that I showed you before. That is the very movie I showed you before. And I have these vapor droplets in this big liquid domain, which are popping out at the interface. And to insult your intelligence, I show you the backward movie, and anyone can see the difference. I get engulfment of vapor bubbles at the surface of the liquid. They go into the middle of it, and they shrink to nothing. So obviously there is time reversal symmetry broken in steady state at the level of observation of that movie. Now, stochastic thermodynamics, which is a field which has been around probably for a couple of decades now, is the proper extension of the second law of thermodynamics to a fully fluctuating description. It tells you not only just that on approach to equilibrium, the entropy production is positive, it tells you what it is. It tells you that the entropy production in a trajectory or in an evolution of the system is directly related to, or the entropy change of the universe is directly related to the ratio of the forward and reverse probabilities of seeing that sequence. So if I think in terms of the movies, I can say, well, here's a forward movie, what's the probability that I see that? And here's the backward ones, and what's the probability that I see that? So I take the log of that ratio and I get the entropy production. So this statement, which obviously has its roots in thermodynamics, for our purposes, we can think of it as it's just an abstract theoretical construct. So I'm not interested in heat flow now. I'm just saying, how irreversible is my theory? And this is the way to answer that question. So the first comment is that the entropy production, and I'm talking about the steady state one now, can depend on the scale of observation. I'll say a little bit more about that in a second. So the very fact is, of course, that in going from, say, a particle theory to a field theory, I have already coarse-grained. So when I calculate the entropy production for field theory, it's not that I'm attempting to capture all of the microscopic irreversibility in the particle dynamics. What I'm trying to do is quantify the irreversibility as you can see it in the fluctuating fields that I'm actually watching. And then the good thing about this, if you look at that log of that ratio, those path probabilities, because I have a Langevin equation in my model B or active model B, I can calculate that thing from the path integral. Here it goes. So the top line here is an equation for the current, which is excuse this rather poorly defined inverse Nabla operator on the left, but the fact is that I can, because the current determines the dynamics of phi, I can calculate the probability of a space-time trajectory for phi of r and t, and I can calculate its time reversal, and I can take the log of the ratio, and I end up with this thing at the bottom here, is that the steady state entropy production in a scalar field theory like this is this object which involves the ensemble average of the time derivative of the field times the non-equilibrium bit of the chemical potential, which can include the zeta and the lambda terms, but I'll only talk about the lambda part now. So that's interesting because it says that the global entropy production is actually the integral of an operator in the field theory. There's the operator. So it's got a phi dot in it, but if I look carefully at what my noise is doing, I can replace this by this object here, which just involves fields and gradients. And so that is interesting too, because actually I don't need to do any dynamics now. If I know the stationary measure, in other words, if I know the probability distribution for phi as the equivalent of the Boltzmann distribution, it's not a Boltzmann distribution, but just that steady state probability for phi, then because I knew what the dynamics was, I can in principle calculate the steady state entropy production for this theory.
Mike?
Yes.
Giulio Larea has a question. Does such a process of time reversal symmetry breaking lead to a first or second order phase transition once phase separation occurs? Or is it not possible to say anything about it?
The phase separation in the models I've been talking about, in those senses, are qualitatively the same as for equilibrium. In other words, you have a liquid vapor binodal, which is first order, except at the very top, there's a critical point, which is second order. So in that sense, the topology of the phase diagram for bulk phase separation is the same as a standard liquid vapor transition. If you have these steady states that have droplets, then the transitions between what we call a microphase separated state, so a state of droplets or bubbles, and the adjacent bulk phase, is also similar to the same phenomena in equilibrium. So that can be first or second order, depending on the circumstances. Okay. Shall I just carry on?
Yes, please carry on.
Okay. So first thing then is that at least at the level of numerics, I mean, it's very simple to evaluate that object as a function of position for a phase separated system. So on the left is a cartoon of a liquid vapor coexistence in active model B with just the lambda term. I do that with the noise. I calculate those averages. And interestingly, there's two contributions to this entropy production. There's a big peak at the interface, which does not vanish when I turn off the noise. So there's a piece of entropy production, there's a piece of, strong irreversibility at the interface between phases, which even in the limit of infinitesimal noise stays finite. And that connects with what I was saying before about having this field theory has somehow managed to create a pump across this interface. It is shifting stuff up the chemical potential gradient, it's doing something which the equilibrium system then has to flow back down, if you see what I mean. So that's where the focus of irreversibility lies, at the interfaces in the low temperature limit, D being diffusion constant proportional to T. But if you look, there's also a bulk contribution which vanishes as the noise goes down. So there's a bulk contribution proportional to the noise temperature, and there's an interfacial contribution which scales independent of it. So in the very last minutes of my talk, I want to just talk a little bit about the idea of applying the renormalization group to this entropy production object. And that contains with it the idea that you could have a system which is active and therefore has entropy production. But you could imagine that if I look at this at some very large scale, I couldn't tell the difference between that and a passive system. And in particular for active model B without the zeta term, but close to this liquid vapor critical point, it's actually very easy to show that that lambda term is irrelevant for a renormalization group. So your first instinct upon writing down model B and adding a term which is irrelevant near the critical point is you say, okay, so I can remove that term at the critical point and I have a good description, but that description without lambda has got time reversal symmetry. So the question is, active model B does not have time reversal symmetry. Is it recovered somehow at the liquid vapor critical point? And just to jump ahead, the answer will actually be no. So anyway, the idea behind this is that depending on if I've got active particles, I zoom in on a particle and I see something like a wildebeest or a colloid, you can tell from the individual local behavior that it's active. If I zoom out far enough, it just looks like particles. So certainly the entropy production is going to go down as I coarse grain. The question is how fast does it go down and does it become negligible in a realistic sense? So I won't show that. That was a movie of some wildebeest, but I don't have time for that. So this is the next 2 or 3 slides, and then I really will finish, a bit abstract, but they're just, the idea of this is that the general expectation that certainly we started from is if I start, I'm talking about an RG structure here, a flow structure. I start at the green dot, point 1, with a system like model B, which has time reversal symmetry, and I then break that. So it could certainly take me to a different critical point. It could certainly change the universality class, or it could leave it unchanged. And by the way, if I'm talking about entropy production, if I have a system like this, which is a fluctuating field theory, so think of the Ising model, kinetic Ising model, there is a natural scale for entropy production, which is 1 degree of freedom, so 1 block spin flips every correlation time. That gives you a natural scaling for entropy production. If those flips are reversible, then I see nothing. If they're irreversible, I should expect possibly to see something of that order. So, okay, so I add the activity. It could be relevant, it could be irrelevant. I do some RG. So I could flow to a point over here, which is clearly active. The entropy production is finite in natural units, but normally you think, okay, this is an active model now. So you'd expect that other things would change, like it'd be in a different universality class from basically the kinetic Ising model, which is what the passive version of this is. Or you could imagine that you end up over there, going back, so you leave your initial critical point, but you go to another one, which is also passive. That's also perfectly possible because in principle, I might have strong coupling. I add these terms. I don't know where I'm going to end up. But actually something else happens, and I'll explain that in a second. First comment I've made already. So if I look at this in d greater than 4, so this is the place where Ising-like theory is easy, this lambda is irrelevant. It's irrelevant in all dimensions above 2, but it's certainly irrelevant near the Gaussian model in more than 4 dimensions. And it turns out it has quite a simple expression there. I told you I can compute it from the stationary measure. Because lambda is irrelevant, the stationary measure converges to that of the Gaussian model without lambda, but the entropy production, which I compute from the average of this horrible composite operator here, stays finite in the sense that it stays order 1 per space-time correlation volume. So that's interesting. It says that, okay, for all practical purposes near the Gaussian fixed point, this looks like an equilibrium model until I look at the entropy production, and then it's finite. So we call that stealth time reversal symmetry breaking. So near the critical point, I end up with a finite entropy production, but everything else seems to be the same as the passive model. So there's an obvious question, which is what happens in less than 4 dimensions. There is a technical obstacle to this. This operator that I've told you about has a lot of gradients in it and a lot of fields. It's very irrelevant. But when you look at the flow of irrelevant operators in RG, you find that you need to treat all operators of the same order together. And unfortunately for active model B, although we're only interested in one of these, which is the entropy production operator, there are 20 operators with that number of gradients and phis. So you have to do a 20 by 20 matrix renormalization group, and that's longer than a PhD thesis. So what we did with that is drop the conservation law. So that then gives me an active version of model A, so-called, which is spin flip dynamics rather than conserved spin dynamics. I still have broken time reversal symmetry. I've now got 7 by 7, and Fernando Caballero, in a kind of heroic effort, did complete this calculation, and it's in this reference here. So what you find then is that that model without the conservation law also has this same behavior of finite entropy production above 4 dimensions and bizarrely divergent below. So the entropy production is bigger than 1 of order 1 per spin flip, or 1 per coarse grain degree of freedom per coarse grain correlation time, which says that there's entropy production probably on all scales below the correlation length. So we're still understanding what this means, but entropy production is there as the quantification of irreversibility in field theories. It's calculable, at least in some cases and under some conditions. It has interesting renormalization group behavior. So I realize I've covered a lot of ground, and I hope at least parts of that were comprehensible and interesting to at least parts of the audience. And thank you for your attention.
Thank you very much, Mike. Let's unmute our speakers and thank Mike for a great talk, and then we'll go to questions. Okay, thank you. Okay, well, Okay, now we're into question time, and I invite you to raise your hands if you have a question. Let me start, actually, Mike. Went by very fast, but how do you keep track of the entropy or the heat or the energy production in this these kinds of sets of equations that you've put forward as model B?
Yeah. So the key thing then was this. I will go back to it because it's quite an important thing. So that is the key thing. So the point is that if you have, and this has the same physics, if you know the fluctuations theorems, the things like Jarzynski's inequality, and there's a number of others. What they're normally written the other way down, the other way around. They basically say, if I see something happen and I want to know how likely it is to see the time reversal of it, all I need to know is the entropy change between the initial and final state to take the exponential, and that's the ratio of those two probabilities. So this equation here is essentially just the inversion of that. It's saying that certainly this is true for any system that does have an equilibrium and heat flow interpretation. It says that the probability of the forward and backward path differ in a way that reveals the entropy production.
But granted this equation, how do you calculate the probability of the forward and backward sequences from your scalar field theory?
So I have, okay, so if I take div of the top equation, I've got phi dot is minus div j, there's a minus sign missing. The current is the gradient of this chemical potential, which includes the non-equilibrium part that I described. So and this got the noise there in the current, as you can see in the top line. So that's a Langevin equation. So I know the statistics of lambda. So if I take that, this piece here over onto the left, then that thing is Gaussian distributed. And that's what this next line says. It says that P is the exponential of this thing. This object here is a property of the path. So basically, what the equation of motion does, it tells me how to turn the noise into a trajectory. And so if I know the weight for the noise, I know the weight for the trajectory in the dynamics.
That's very cunning. Thank you.
And if you expand that square, what happens in between the forward and the backward path is that the only thing that changes is the sign of this term. And so all I'm left with is 4 times the cross term between phi dot, or this inverse nabla on phi dot and nabla mu. And then those nablas cancel off by integration by parts. I'm left with this thing.
Okay, very nice. Okay, there's some other questions. Victor Yakovenko has a question. Victor, if you unmute your mic.
Yes. Yeah, so I have this question. So roughly speaking, you started with equations of motion, so to say, and then you derived entropy production formula. Can you do it the other way around? That is, postulate some form for entropy production and then derive equations of motion by maximal entropy production or something like this. Because you said the notion of free energy is kind of not applicable because it's non-equilibrium. But there is this idea of maximal entropy production. So can you postulate entropy production function and then maximize this entropy production and obtain equations of motion in this way, kind of doing it in the reverse direction?
I think that's a very interesting question, but I think you see, if you look at the form of this, there's a lot of information being lost here.
Yeah, sure.
So because basically only these cross terms in those path weights matter. So I don't think there's any way of uniquely reconstructing a theory from knowing this about the entropy production, for example. And so there may be some other principle, like some Bayesian principle, which would say, well, this is the least informative theory that gives you that structure. But I've not thought about that, and it's an interesting question.
So basically, at this level, the principle of maximum entropy production by itself would not be sufficient. Doesn't have enough information to have the full description, basically.
That's certainly true, and I'm not even sure that there is such a principle for this type of theory.
Yeah, that's I was wondering if there is. Okay, thank you.
Premi has a question.
Yes. Hi, Mike. I enjoyed your talk very much. are there any observable consequences for experiments on active matter from your approach?
Well, so there's lots of observations of active particle systems, particularly in this self-propelled colloid domain. And so, for instance, among these, you do see these microphase separations. You do, I mean, one of the movies I showed you was that in the active Brownian systems, you see these voids inside the dense phase. And there are at least some experimental systems, which obviously are not exactly the same dynamics as active Brownian, where strange phenomena like that are seen, and certainly ones where this arrest of phase separation in at a finite length scale is seen. So, you know, obviously the kind of theory I've talked about, what I didn't talk about at all was a separate set of attempts of explicitly constructing theories like this by coarse graining more microscopic pictures. But I think the strength of this approach is that it at least tells you that certain things are going to be generic, and so that you shouldn't be surprised when you see them. In other words, something where you would not see in a passive system, you do see it in the active one. So I think the connection with experiments is more there than with any attempt to predictively model outcomes for specific experiments, because we don't have enough control of the coarse graining to say this microscopic dynamics translates into these parameters of the model. Okay, or indeed whether the model is really like this or not.
Thank you.
I should say, by the way, as you know, that we do have models of this which are not based on the 5-4 theory, but you know, have rho log rho free energies, more like a liquid state theory. One of the things we learned, though, is say when we were looking at this reverse Ostwald regime, if the structure of the model isn't the simplest you can make it, it's almost impossible to calculate anything. So, for instance, that way of constructing the getting from the funny chemical potential to the growth rates of droplets, I mean, this we really did need the simplest model we could have to be able to get to the end of those calculations.
And as a follow-up, in your last slide, you mentioned that you studied the simpler model, and then you had the intuition that the more complicated one, the 20 by 21 with the 20,
yes,
would behave similarly. I didn't quite understand where the intuition came from.
Yes, well, it basically just comes from the structure of the RG as it is. So you have this, what happens when you look at, and this is something I didn't know, by the way, before Fernando did these calculations. If you look at the scaling of irrelevant operators in RG, you get these basically set of eigenoperators, which are some linear combination of all the operators of a given order. Mm-hmm. And you can, the leading divergence of some observable depends on its projection onto the eigenoperator with the least irrelevant exponent. So which vanishes most slowly as you approach the critical point. And there are certain aspects of that you can see in the structure of the equations for the 20 by 20 system, but then you can't actually calculate the exponents in the epsilon expansion. So you sort of know it looks similar, but you can't really get the answers out. So that's where we were with that.
Okay, thank you.
Good. Are there any other questions from the audience? Okay. All right, if there are no other questions, then let's thank Mike one last time for this fantastic and very clear talk. It was great. Thank you, Mike.
Thank you.
Good. Well, everyone, this ends today's activities of the ICAM Summit. And tomorrow, the science sessions will resume at 10:30 in the morning Eastern Daylight Time. And there will also be, for those in the ICAM Science Steering Committees, we will be starting our general meeting at the early hour of 9 a.m. Eastern Daylight Time. This is a killer for those on the West Coast. I apologize for that, but it allows people in Asia to also participate in the meeting. So look forward to seeing you all at the science sections tomorrow, and also those of you who are coming to the ICAM general meeting. And thank you very much. And once again, thanks to Mike and all the other speakers today. It was a very interesting meeting.
Thanks, Mike. It was nice seeing you again. It's Laura.
Thank you. Thanks, Laura. Thank you.
Very nice talk.